All right, let's see. Things seem to be working fine. All right, hello everyone. As usual, if there's any issues with sound, video, whatever, please write about them in the chat. If there is no issues with either, then you can also write about this in the chat. So, an important disclaimer. Somebody asked me this on Twitter. This is a common point of confusion, and today there might be two common points of confusion. So this is not an Unreal Engine stream. Nothing that we're going to talk about today overlaps with Unreal Engine in the slightest. The name of the project that we're going to be working on today, unfortunately, coincides with the name of Unreal Engine Particle System Technology, which I should have thought about at the time. I think it already existed, but the project started in 2018, so, you know, whatever. It's been many years. It's fine. For people who are new, there is a renderer on GitHub that we have been developing on stream on and off for the last many years. The streams are irregular in nature because they happen whenever, you know, there's stuff to talk about. And then a couple things. So the last stream I think was in August or something like this year. And then I didn't really have anything new to talk about, but then kind of two things happened. One is sound is pretty quiet, is it? I guess I can like do this. And I can also move the mic. Maybe I can't move the mic. Let's just keep it like this, okay. So there is two things that happened since the last stream. One is I went to a wonderful conference in Netherlands and met a bunch of people who, you know, watched the past videos and said, hey, you know, it's cool. Are there going to be more videos? And then the second thing that happened is there's some things I want to work on at some point in the future that this renderer would be great as a baseline for experimentation, but there's a couple things that I wanted to change. And so specifically today, what I want to talk about and work on is making the loading time of the scene faster. And I figured this would be also a great opportunity to talk a little bit about the CPU profiling, show you Superluminal, and just, you know, I don't think there's been 30 videos on this so far. I don't think we've touched on the CPU like performance profiling optimization aspects once, which is kind of unusual in this field of work. So today might be a good time to remedy that. So all right, so let's just quickly think about, okay. So let's talk about what we have right now. So what we have is we can run our code and it can load a GLTF scene. In this case, it's bistro scene. And then we have like camera control, we can fly, we have shadows. The geometry is rendered using rasterization. And then the shadows are using ray tracing. And then we even have animation supports, which we hacked into the GLTF file. So I can press a space bar and have the bike sort of move a little bit. Now the issue is that when I run the code, it takes a few seconds for it to load the file. And it takes, the amount of time it takes sort of depends on whether it's a hot load or cold load, as in whether some of the data is in cache or not. So I want to first look a little bit at the profile and kind of talk through what we could do, what we should do, and stuff like this. To do that, I'm going to be using Superluminal. So Superluminal is a commercial tool, but it's a fantastic profiler. It's available on Windows, and it's not available on Linux yet, but I have a special build that I'm going to be using today, which runs on Linux. I don't know when it's going to release on Linux, but hopefully pretty soon. It is very, very nice. On Linux, it's whenever it gets released, it's a kind of different category of profilers that hasn't existed on Linux before. And sort of the same is true on Windows, but maybe on Windows there is, on Windows I know there's PIX, for example. I haven't really used PIX CPU profiling, but it's hard for me to talk about the Windows profiles as like a general set because there's many of them. They have different properties, but Superluminal is unique in certain ways, and on Linux, without Superluminal, it's a little bit difficult to profile some classes of applications and, most importantly, real time. So it's used widely in games industry, but it is a commercial tool. So if you're a hobbyist, a license costs some amount of dollars, I don't remember. And what we're going to do is we're going to run the code and then look at the profile. Now, one caveat is, as I mentioned, the time it takes to load the scene sort of depends a little bit on whether the files have been loaded before, whether they're in the cache. On Linux, you can empty the current contents of the memory that caches the files on disk using this descriptive command. You like write one to a file that is not a real file, and this tells the kernel to drop the contents of the memory page cache. So we're gonna do this. I've never tried this before on stream, but I don't think it should like break the stream in any meaningful way. Maybe there's gonna be a hitch, whatever. But the reason why we wanna do this is we won't do this often, but I wanna run the profile without the page cache first, and then kind of have the second run of the code after that. Tracy is a different class of the profiler, so it's a good profiler, but although maybe they also I haven't really used Tracy much, so maybe Tracy gets close. I don't actually know. Superluminal doesn't have GPU profiling in it, whereas Tracy has some integrations for GPU captures. So I think the reality is you probably want to use multiple different profilers. For example, right now on Linux, I use Superluminal, I use Perf. And then I occasionally use AMD uprof, it's called, and different profilers. And then for graphics, I use Nsight because right now I have an NVIDIA GPU. If I had a AMD GPU plugged in, I would use AMD's Radeon graphics profiler. You usually need like multiple different profilers for multiple different reasons, unfortunately. But yeah, I haven't really used Tracy much. Tracy is open source. It requires a little bit of integration. Anyway, so let's run our code. Oh my God. And so we are going to run it twice. First, and we are only interested in profiling the loading process. So I'm going to like terminate the application immediately after it starts. So as you saw, it took like a few seconds. It took longer than what it took when I was running it in the beginning. So let me run this again. And then I'll have two profilers, and then we can look at the two profiles, and then we can look at the two profiles and sort of see how they're different. But let's look at the sort of first one first. The heck? Okay, so the general idea in these profilers is that you see a timeline. So unlike the traditional sort of sampling profilers that you may be used to that just show you the statistics of the code, these profilers show you the timeline. So, the application started, and then every row is a thread. And then within every thread, green refers to the CPU activity and red refers to synchronization, which means we are waiting for some mutex or something like this. Most of the threads in our process are not ours. We don't really multi-thread our code right now. But we use Vulkan graphics driver, which on our behalf may spawn some number of threads. We use the windowing system, which on our behalf may spawn some threads in our process. It's pretty typical to see more than one thread once you start using these like systems or graphics libraries in your application, even if you haven't created them yourself. There's some activity in one thread that's not ours, which we're gonna ignore. And let's look at, then in Superluminal, what happens is you can look at the activity like inside the thread, and it will show you the samples that it took. So Superluminal is a sampling profiler. I didn't have to change our code in any way. You just run it on the binary, it just shows you stuff. But the things that it shows are simultaneously sort of sampling-like and instrumentation-like, in the sense that it will show you, it will collect the samples. So it samples the execution of your program at like 8,000 hertz or whatever. The this is part of the options. Yeah, so the default frequency is 8,000 hertz, so 8,000 times a second, so 8 times per millisecond. It will sample the stack of every thread. But then what Superluminal specifically does is it will show these samples in a form that resembles, if you've ever seen instrumentation timeline profilers or flame graphs are somewhat similar too. It will show you like these call stacks that hierarchically aggregate the function calls. The other thing is it will show you both user space and kernel activity. And also, because it's not instrumentation based, but because it's based on like resolving the symbols to the extent that it has symbols, it could show you parts of the kernel code and parts of the driver and things like this. So to the extent that you have symbol names for the stuff that's running on your computer, it will show you a pretty detailed picture of what actually happens. So let's look at the first profile, and let's kind of look at the timeline, right? So our process starts, and then it takes like 300 milliseconds for it to actually get to our entry point. Important note, so this is the cold run. I dropped all of the caches. This means that potentially, for example, system modules, graphics driver binary, like a bunch of things could be evicted from the cache when I did this. So this is an unnaturally long sort of start, and usually the process starts faster. And also there might be some extra like profiling overhead around the start of the process specifically. So I don't want to dwell on this too much, because our focus is really on the scene loading today, where we do the bulk of the work ourselves. But just, like in terms of what things happen, so there's some GLFW stuff, and I will look more closely at the times in the second profile, because I don't know to what extent, again, this is like, oh, we are loading a DLL, and it takes time because it's not cached, but it usually is. But so we are creating the window through GLFW, which does like a bunch of horrible things because Wayland is weird. And then there's some gap of some stuff that we are doing in main. And then we are creating the device, which takes a bunch of time, and it's all inside the NVIDIA graphics driver. And if you look closely at what happens here, you can kind of, inspect this code and ask questions like, why is libcuda.so taking any time during device creation if you're not using CUDA? But, it's kind of besides the point. So then there is some memory allocation for graphics resources. This create buffer takes a lot of time for some reason. We're going to talk about some of this stuff maybe later in the stream as we go through this. So then, like, our actual code starts, so to speak. So we are loading the GLTF file, and that process takes 3 seconds approximately. During this, we do the actual loading of the file, which is like here. So it's like 12 milliseconds to parse the GLTF binary or GLTF structure. And then we load the buffers from disk. So this is the example of, okay, so this code, I'll show you the file structure in a second, but this code loads like a large binary file from disk, right? And because the file is not in the cache, we have to actually load it from disk, presumably. And so we can look at kind of what happens in it. We do a libc read call. It emits a syscall. The syscall goes into the kernel goes into the ext4 file reader code, because we are using ext4 file system, and then it goes into the page cache implementation, and then it tries to get the pages, and then it schedules IO for every page, because we don't have this in the page cache, so we have to load it from disk and stuff like this. Interestingly, this process is quite CPU bound. If you look at this, we are loading like it's maybe 100 megabytes or something like this from disk. you would normally expect that because the file is not in the cache, we're like spending time sort of waiting on disk activity. But interestingly, if you look at the green to red ratio here, just eyeballing it, like half is waiting and then half is like running actual code, which is typical. I don't think we'll get to this today, but loading things from fast SSDs is difficult these days because fast SSDs are faster than what the operating system sort of expected when the code was written. And so it's typical to sort of not be reading the file at the speed that you're expecting it to be read. Or actually, since we're here, so let's just look at what we are actually loading. So these are the two files that we are loading right now in that sort of load scene call. The GLTF file is a JSON file, which is fairly small, it's like 2 megabytes. But then most of the actual data, the vertex data, the index data is in the binary file, which is like 100 megabytes, as I said, right? So it's a 100 megabyte file. We are reading it in a single read call from disk, and it takes us 100 milliseconds. From this, you can immediately ballpark the performance of this loading. It takes 100 milliseconds to load roughly a 100 megabyte file, which means it will take a second to load roughly a 1 gigabyte file, which means we are loading at 1 gigabyte per second. This sounds like a lot. It's actually bad. My SSD is rated for, I forgot, multiple gigabytes per second, maybe 3, 4, something like this. So this is actually like worse than what we would expect to be loading at. And there's multiple reasons for this. I don't think we can actually get to trying to fix every possible issue. So there's a difference between making the loading process optimal, as in there's nothing to squeeze out anymore, and making it faster. Today the goal is to make it faster, not necessarily optimal, because optimal is difficult and takes a long time. Anyway, but so after this is like 100 milliseconds. The elephant in the room is, of course, that it takes us 2.5 seconds, a little bit more, to process the scene. We can look at the individual calls, and what happens here is a lot of the so we take a mesh, we copy some stuff somewhere, then we build the meshlet data, we compute meshlet bounds, we run simplification code, etc. Important note for people who haven't really seen this project before is that we are not just loading the data from GLTF file and rendering from these buffers. We are doing multiple important optimization steps, but including among them are things like generating level of detail, which is absent from the GLTF file, and also building the meshlet structures. That also takes time. And so all of this is kind of generated from the GLTF file on the fly, or as we are loading it, which is why all of this takes time. So you can look at the individual meshes and you can ask, okay, how much time sort of individual calls take and stuff like this. But because this scene has many meshes, at this point you really want a summary view. So what Superluminal does, this is not a Superluminal ad, this is not sponsored by Superluminal, etc., although they did give me a copy for free. But you can, if you select a range in Superluminal, then it will aggregate the actual timing information for you. And so we can ask, okay, during this load scene process, what actually took time, which is in this view. And so we can say, okay, so there is some amount of time that just loading data from the GLTF file took, like this is this unpack float and stuff. And then if you look at the actual process of adding the mesh to our internal scene representation, then we look, okay, so like 30% of time is simplification, so this is level of detail generation, and then roughly the same amount of time is meshlet construction, and then we compute the bounds for the individual meshlets, and then we also optimize our vertex cache, and we optimize the meshlets individually. So there's like a bunch of things here, right, that all have to happen. Okay. So this is the scene. This is going to be the focus of today's stream, like removing this. And then there's also the texture stuff. The texture stuff I thought maybe we can get to today, but I think it's unlikely. We need to write some code for the scene stuff, and it'll probably take a bit. But let's just look at load image, because I think load image is going to be instructive to compare in this capture versus the next one. Because when we load the image and we are starting sort of without the cache field, then we can look at the summary. But so I guess the first thing is, so image loading ends roughly here. So it takes us around 2.4 seconds, roughly the same amount of time as the scene loading, to load the images. So the images are on disk in the DDS format. So these are DDS files, and they're internally compressed using something, BC7 maybe? I don't actually recall, some texture format. But if you look at what's actually taking time here, then instead of the actual, like processing, so I'm going to ignore this for a little bit and just look at some other image, because there's complications in the profiling process I don't really want to talk about right now. But if you look at like an individual image, then we see roughly the same picture that we actually just saw in the binary buffer, where, okay, we are calling fread calls the ext4 file read in the kernel, and then it calls the reads, and the reads do scheduling of IO operations. And then in this one, we see, I'm not sure if there's a way to summarize. I don't really see off the top of, I'm sure it's somewhere. It would be, I was looking for like a number that says, okay, in this time span, this percent was spent waiting, this percent was spent executing. I don't really see that, but maybe hover on this will show. Okay, yes. So in this sort of selection, we only spent 20% of time running CPU code, and then 80% of time just waiting. And so basically in the individual textures, we're mostly just waiting for the for the disk, right? We can do the similar ballpark estimate of are we actually doing this quickly. So hold on, I think let's do this. So it takes us 2.4 seconds to load all of the textures from disk. Let's assume that we are loading every single file in this textures folder. I don't remember if this is actually true, but let's assume it is. And let's try to quickly figure out. Okay, so we have roughly 967 megabytes of textures. So it's approximately a gigabyte of textures, very nice. And approximately a gigabyte of textures takes us 2.4 seconds. So whereas on that binary file, we seemed to be taking, we seem to be loading with roughly a gigabyte a second. This one, we have a gigabyte of textures and we load it in 2.4 seconds. And so we are way less efficient than what this should be able to do, right? So this is not great. Part of the issue here is that there was a 100 megabyte binary file for geometry, and then many smaller files for textures. And then each individual texture has probably more overhead, and there's less read ahead that the driver does for us and the SSD does for us and stuff like this. So again, we're gonna probably not get to any of the image stuff today, but this is something to keep in mind. Essentially, okay, it actually takes us a while, much longer than what the hardware should be able to do to load the images. But let's focus on geometry, because, so if you look at the second profile, so the second profile is I just ran the same thing again, right? No code changes, just run it again after the first run. What happens here is that all of the data should be cached in memory, because it's like a couple of gigabytes and I have a lot of gigabytes of memory. And so if you look at the image loading here, it only takes 300 milliseconds. So it's like 10 times faster, more or less, than in the uncached version. And if you look at what happens during the texture loading, it's all CPU activity. Well, not all CPU activity, there's still non-CPU activity. And if we look at the image loading process here, then we see a very different picture, because instead of just being dominated by the sort of loading from the file, we see, okay, so we create an image, creating an image requires a memory allocation, which goes into the driver, and it takes some time to create, to like allocate memory. And then we do the actual read. The actual read is very fast. Why? Well, because the actual read is just copying data from the page cache in memory to wherever we are reading it to, right? And then we have some more driver activity. And the reason for this is that our image loading, and this is where we actually, so you can see during the allocation, the thread is active, so that the CPU is doing work. During the file read, it's also CPU bound because we are just copying data from page cache to our own buffers. And then what happens after this is that we schedule a GPU command to upload the data and then wait for it. And we do this after every texture. And so you see that we are then waiting for, however much we are on the upload to finish. And then let's just look at the summary stats. I'm trying to go through this quickly because I don't actually want to work on the textures today. But so if you look at the profile during the sort of cached run, right, and look at the summary, then we see, okay, the actual read, so copying data from page cache, only takes a quarter of the time. And then allocating the memory from the graphics driver takes 14%. And then almost half, 40%, is the just waiting for the GPU to copy data from one place to another. So this is also like super inefficient. At some point we'll do something about this. But if we look at the actual scene loading process here, then it takes roughly the same amount of time, like 2.6 seconds as it did before, because it's mostly CPU bound, and it's because it's mostly us just doing, all of these geometry operations. And then if you look at the actual loading from the file that happens at the beginning, then we see it takes us like 40 milliseconds to load the 100 megabyte buffer. And it's because it's just copied from page cache, so, and then if we ballpark, okay, this is harder to ballpark. So it's 100 megabyte and it takes us 40 milliseconds. So a gigabyte would take us 400 milliseconds. And so this is approximately 2.5 gigabytes a second or something like this. So this is also not great. This is also not the speed that you would expect memory copies to run at. But this is complicated by other factors that we probably will talk about like later in the stream. So that's the general picture. Now, what do we do about all this? So the big reason why I want to optimize all of this is there's two reasons. One is just I think it's like instructive to do. It's, there's like fun things to talk about, but also sort of selfishly, whenever I work on improvements in this code, it would be nice for this code to take less time. For this scenario, the main thing we are interested in is actually this run, because you're repeatedly running the renderer, you're like improving something, you change some Vulkan code and you want to run the renderer again. And it would be nice for it to take less time. So in that sense, the geometry is our main problem, because although in uncached run, both geometry and texture loads take roughly the same amount of time, in cached run, the texture loads are less of a problem, much less of a problem, and the bulk of the problem is geometry. Now, there's generally three ways that you could tackle this problem, and we are only going to do one of them. But let me talk about that. Let me first. Oh my God, no. Okay. So the problem with docking layouts is that if you accidentally disconnect a dock, you are stuck. I have no idea how to redock this thing back. Oh no. Okay. No. All right. Docking code does not work very well here yet. That's Linux for you. Okay. Can I just close this? What are these buttons? Okay. All right. I pressed some button that was very tiny and it did what it was supposed to do. It's probably Superluminal people are watching this. I have no idea what I just did, but this was not obvious. So I want to talk about the three possible routes that we could take here. Let me first look at chat. So I covered the sampling rate. Yeah, so the dropping of the page cache likely caused the stream irregularity. That makes sense. Yeah, thread interaction, perf has flame graph, visualization. Yeah, so the blah, blah, blah. Okay. Yes, so 1 gigabyte a second is slow for an SSD, and as I said, this is not the SSD's fault in this case. Well, slow. If you have a modern SSD that is an NVMe SSD, then it is slow. If you have an older SATA SSD, then it's actually pretty fine. But yeah, this is not fast, but it's a little bit difficult to be fast for a few reasons. So I don't think that we'll have time to talk about this today. So what could we do? So again, we are going to ignore the texture loading and just focus on geometry. What could we do? Oh, I wanted to mention, right, so there was a comment around thread interactions. I don't know if there's a way to show this well here, but yeah, so Superluminal has like a bunch of features that make threaded profiling more useful, more sort of accessible. It's the thing that we are seeing also here, one important point. This thing is very different from perf flame graphs. Why? If you've seen a perf flame graph, I don't have it sort of, I don't have anywhere handy that I can show one, but if you've seen it, if you've seen a flame graph, you know what I mean. It's a list of bars, and you know, there's bars that contain other bars and stuff. The crucial difference is that flame graphs in perf display you aggregated information about performance, whereas this timeline view is not aggregated, it's a timeline visualization. So when I go into append mesh, notice how there's multiple calls. These are not necessarily directly related to the number of calls that we actually have in our code, but let's ignore that. We can look at what actually happens in that flow, right? So, okay, we call append mesh, then it calls generate vertex remap, then optimize vertex cache, and then optimize, and then rescale, and then build meshlets, and optimize meshlets, and then there's some step vector stuff and stuff like this, right? So this is like what happened in your program, or how the profiler saw the execution of your program over time, as opposed to an aggregated view. Sometimes an aggregated view is better, sometimes a timeline is better. If you want an aggregated view, as I was showing, Superluminal provides this, it just doesn't, oh, I think there, is there? No. In some profilers, you can like toggle between the tree view and the flame graph view, but they are really identical. They show you the same information, right? But this is different information just qualitatively. So yeah, anyway, okay, so what could we do? Well, there's kind of three ways in general to deal with stuff like this. Option one is to optimize the code, as in look at what actually is taking time and look at what the function is doing and try to find inefficiencies, either algorithmic inefficiencies or, you know, something else, like some machine level stuff like CMD or whatever, and like make it faster. If we look at what takes time in append mesh, most of these are mesh opt functions. This is part of the mesh optimizer library that I develop and maintain. It's pretty well optimized, you know, there's like always stuff to improve, I'm sure, but it would be surprising if right now on stream, I could just look at the profile and be like, oh, it is very shocking what this code is doing, because it's clearly inefficient. Because, you know, obviously I've looked at all of this stuff like many times over the years and optimized things. If you're interested in kind of related commentary, then by capital letters, then I have a blog post from September that kind of talks about adjacent problems, because it talks about similar processing but more involved, that took more time on a larger scene, and sort of some things that I did to optimize, and it has some Superluminal stuff too and stuff like this. So and this talks about kind of two of the possible ways to deal with this problem. So so one is just like look at some code and try to optimize it. We're not going to do it today because again it's like, you know, it is very possible that the code that is calling the mesh optimizer functions here does something stupid, because, you know, like, who knows, it's been written over the years. I didn't pay that much attention to the time the code takes to generate things, but so like it's always possible. But it would be surprising if we could accelerate the underlying functions, and, you know, if you look at the time things take, then most of the time is inside the mesh optimizer functions. So we're not going to be doing that today. The second thing you could do in situations like this is actually use multiple threads, right? And this is very convenient for our use case, because if you look at these sort of function flow, right, we have append mesh and then append mesh and then append mesh, and, you know, if I think this scene has something like 500 meshes. If I remember correctly, we can kind of try to ballpark this. I think these are mesh attachments. Yes, these are instances, but okay, that's fine. So if you look at the mesh indices in the GLTF file, yeah, I think they max out at like 500 something, basically, more or less. 527, whatever. So 549. So there's like approximately 550 meshes here. We have 16 threads with 32 threads on 16 cores or whatever on this system. So of course we could just run these on multiple threads. Now, I don't want to do this because the third way to make something faster is to stop doing something. Nothing is as fast as not doing anything at all. And in this case, probably you want to do two things. So I said there's three possible ways that we could optimize this code. You know, one of them has already been done by proxy of me optimizing Mesh Optimizer over the years. And then we could do multi-threading and then stop doing things. Ideally, you do both. So ideally, you multi-thread the code. And that alone would substantially reduce the time. So if it scales perfectly, which things never do, if it scales like 10x on 16 threads, then this would be 250 milliseconds instead of 2.5 seconds, which is way better. But I want to do something else because you know, it's just not, I don't know, I already did multi-threading work for these blog posts that you can read about, and it's, you know, fine, and there's like some fascinating problems with this that you have to solve and whatever. But from the structural perspective, if you think about how a game engine that is actually optimized for the hardware it runs on should work, you never should do the thing that we are doing. You never should do data preparation after loading the GLTF file, like every time a user starts your engine, right? Like this just should never be the thing that you do. What you have to do, what you should do, basically always, is change the data representation offline, take the GLTF files or whatever you have, pack them in whatever format you think is optimal for the hardware, and then load that format. Now, that makes content iteration more difficult. So you could see sort of a different flow where, how do I put this? Or during development, you could see like various versions of the flow, right? During development, you could see, oh, I have this offline process that runs separately. You could also see the engine loading a GLTF file and then processing this and then caching the results. So we're going to do the latter, but they are kind of the same thing. Essentially, what we need to do is we want to take this code and split it into the code that prepares the data from GLTF and then saves it to disk. And then the actual loading of the resulting data from disk should be much quicker because we don't have to run all of this code. And that will help us in the sense that in the future, if we need more complicated, more expensive data preparation. Because yes, right now, you know, we could multi-thread this code and it will take and run in 250 milliseconds and stuff, and it will be good. But what if the scene is 10 times larger? Okay, suddenly it's again multiple seconds of waiting every time. What if the algorithms that we need to run during the pre-processing take more time? So in general, it's always good to have the separation between sort of preparing the data in the optimal format and then loading from the optimal format. We just have never had this separation because of how this code historically evolved, I guess. But that's the plan. In game development, this term has different names. One of the possible names is cooking, which is why the stream is called Cooking Geometry. There's not going to be actual cooking on stream. If this has not been clear by now, then, you know, I don't know. All right, so let's do this. So then our goal is basically look at the data that this function produces and then serialize whatever it's producing to disk, and then replace the code that loads it with the code that just loads that from disk. And that's kind of it. All right. Yeah, so there is a question, which is, if you have the file, if you have the contents, and then you process the contents, and then you save the result to disk. If you think about this as a cache, then there's a question as to kind of how do you figure out if you should invalidate this cache. What you can do is you can indeed, as somebody's pointing out, hash the data. But our goal is optimal performance to the extent possible, right? And the optimal thing to do this validation is to do nothing, because then, you know, you spend no time doing this. Because if we did have to spend time doing this, then we still have to, you know, like load this binary file and then hash it and stuff like this. We can just we can just compare like the modification times and stuff like this. Is generally sufficient for this use case with some caveats, but I don't want to spend too much time on the invalidation portion of this, neither in sort of the code that is doing the invalidation should be fast, but also I don't want to mull over, you know, oh, how should I detect if the file changed? Yeah, we'll detect somehow, it's fine, it doesn't matter. Oh, the other thing, so the other reason to do the separation is that it allows us to figure out what's the better way to load data in a more direct fashion. So for example, right now, this function, for the sake of like code organization and stuff like this, let me switch to the editor. So if we look at like what the code that is running is actually preparing, it's preparing this data which is in like stat vectors and stuff like this. This is not the most optimal way to do this, but if we pre-process things, and you know, we can remove STL from this, it'll take a bunch of time, it has its own caveats, I don't know, it's like all, after you've like removed STL 1500 times over the course of your career, things like this stop being exciting. But once you have the data like on disk in the form that's actually just straightforward, like, you know, binary blobs of data, then there's better ways to directly load it into the GPU memory. You don't have to think about like STL and like vectors and stuff like this. You can like mmap the file, you can figure out how to, on modern GPUs, there's a feature called rebar, which allows you to map VRAM into this process memory as like just writable data. And so in theory, you could like map the file, rebar map the video memory buffer and like mem copy from one to another. And it's direct, it may not be fast, we'll find out. But there's better ways to deal with this once a data structure like this. Anyway, so that's the plan. Now, it's already been 44 minutes and we haven't written a single line of code. So let's try to write some code as quickly as possible to sort of to do this optimization that I'm talking about. First we'll just write some code to write the data that we have loaded and prepared and stuff like this into a file. Let me I guess I'll create a new file. Actually, I don't think I need the header file for this necessarily. I'll just put it in this file for now. And in the usual spirit of the streams, we will cut corners, we will like skip error checking, we will, you know, we need to write some code. We don't have time. So the first thing is, let's just write some code that saves the data to disk. And then we'll need the code that loads the data from disk. In fact, yeah, okay. Right, important point of clarification actually, I forgot about this. So we have this geometry struct that has the actual geometry data, but when we load the scene from disk, we also fill a bunch of other stuff. And so we'll need all of this stuff, you know, when we like load it from disk as well. So yeah, okay, so for now then, okay, so for now let's do things like this. Actually, let's just duplicate basically so we have data that we can load from GLTF, so then we need to be able to save it to a given file, and we'll just save like all of it exactly as, you know, as specified. And then camera, send direction, and that's it. And then we can just do the same thing during the loading, where we take the path and then we load geometry materials, draw calls, texture paths, animations, cameras, send direction from it. Okay. So then we just need to basically implement these two functions. And then there's gonna be issues in the, you know, like when we load from, in this interface, it's inefficient because when we load from the file, we still are writing data to these STL structures, which is not ideal for performance. But we're gonna ignore this for now. Oh, and actually, let's, I'm worried about time. Let's skip animations for now, and let's just deal with that separately at some point. Because animations have this two-level like vector stuff that I don't. I guess we can, let's just ignore animations for now, just to keep things simpler. We'll come back to this if we have time. So yeah, so like that's just the plan, right? Like how do we load and save this from the file, right? So initially we will just use the normal like file star operations without any like tricks or anything like this. Is not going to be the most optimal way to do this, so we will come back to that too. But let's just take things one step at a time. The way I like writing code is, you know, we have code that works right now. What's the minimal modification to that code that still works but gets us closer to, you know, where we want to be? I mean, I guess it should also return a boolean, because who knows. So to write it, we'll just open the file, the target file, and then, you know, I guess we can do error handling. The other thing that happens with these cache files is, how do you know that what you're loading is data that you can safely load? We'll also mostly ignore this because validation for safety of files takes time. and you know, we're trying to save time, so we will ignore that too. So how do we write this data? Like, what format do we use to write this data in? The most straightforward way to do this would just be to have some sort of header that we write to the file that describes the data that we are writing, and you know, has ideally offsets to either has offsets or sort of or has data that makes it easy enough to compute offsets to the data that we are saving. But so let's do that for now, and then we will come back to, you know, improving this. There's like many different ways of how we can sort of implement all of this, but for now we'll just do the most basic bare minimum form. So the most basic bare minimum form looks like this. We have a couple fields we need to save, such as camera and sun direction for some reason. We will come back to some of the framing, but I just want to sketch this out like in its sort of current form. So then we need for every vector that we are saving, which is these guys, but also this, and also this, and also, oh, that's annoying. So everything that is not like a fixed size structure gets a little bit annoying. Some people have serialization frameworks to make dealing with things like this easier. We obviously don't have a serialization framework and will not write one or use one. But initially for the first cut, just trying to figure out what's the best way to organize this. The way I like dealing with formats like this is using chunks. But I'm trying to figure out if I should immediately invest in chunks or if that's a bad idea. Actually, yeah, that's fine. So let's hold on. The simplest way to write this code is literally just to write a length for each one of these, and then just dump the data like one array after the other. It's going to be a little bit messy though to deserialize it after this. Or not to deserialize, deserialization actually will be straightforward. It's going to be a little bit messy in the sense that making changes to that format is going to be annoying. But maybe that is fine for now. Let's actually, okay, let's start with the simplest possible thing that can work, and then we will iterate from there. So the simplest possible thing is basically save the number of elements in every single array. And then, you know, save the data for every single array separately. And then we have this annoying thing that mesh count, that the vector of strings is, you know, like requires us saving the number of strings and then saving each string somehow. And the reason why we need these is because my goal is to not have to read the original GLTF file at all, and so we have to unfortunately preserve every possible piece of data that, you know, that is carried in the GLTF file. And obviously, if we don't have the texture path, then we can't load the textures, and that's going to be unfortunate. Maybe we'll just, so for simplicity, we'll just save every string as like some fixed size, I don't know, 128 byte or whatever. Value, and we are gonna rework a lot of this in the future, but for now let's just do this. All right, So let's just try to, I'm gonna use Copilot to like generate a bunch of this boilerplate code, which is what I'm doing right now. I just have it set in like a mode where I have to press a key to activate Copilot because I usually don't use Copilot. But for the sake of this stream, for sure, it's gonna save us time. Okay, so we are gonna write a bunch of sizes of all of these arrays, and then for every one of these arrays, we are gonna write each one to the file. It's gonna be funny if Copilot like writes most of the code in this stream for me. But it's honestly faster than like, okay, so this is garbage, we are not gonna do that. But let me look at the first stuff. Vertex index, meshlet, meshlet data, meshlet vertex, vertex meshes, materials, materials, draws, texture paths, camera and sun direction are in the header for now. Okay, cool. So, when we are writing things, a good property of a binary file that holds data like this is that you can jump to the section that you're interested in without having to like parse the whole rest of the file, which is the big reason to dislike the style of serialization of a vector of strings, where you write a length of the string and then you write the data of the string. Because then for you to get to the string number 7, you have to have parsed out of the binary file the strings number 1 through 6. So this is bad. We are not gonna do that. Also, we don't use auto in this house. So instead, what we'll do is we'll just write these as 128 byte characters, and then we like string copy or something. And then we will come back to a bunch of this stuff later. But I think for now, let's just write things as like fixed size buffers. Okay, so this might be a good first cut. We're gonna rework some of this in a moment once like all of this actually works. The other difficulty about what we are gonna do right now is that actually when we are preparing the data for rendering, we are not just preparing it for like one. There's a few configuration variables basically that affect how we are slicing the meshes into meshlets, and these configuration variables are important because if you bake the data or cook the data, whatever, for one configuration set and then try to use it with shaders that expect another one, bad things will happen. So if we look at the configuration file that we are using for all of this code, there's basically two critical variables that we need to keep sort of consistent between the cache and the runtime representation, which is this maximum vertex count and maximum triangle count in the meshlet. So let's store them in the meshlet as well. I don't know why these are all... Do we really care is the question. Let's do using size t in a sort of in a thing you save to disk is bad practice, so let's not do that. And then let's put this stuff here because I want to move it out in the future. Okay. So yeah, so let's just store like meshlet max vertices and triangles. And then we will fill these from config file. All right, so this goes here, and then what the hell was it called? Mesh max. Oh, I have to include it, I guess. Okay. All right. And these we will just use so that when we load the file from the cache, we can say, hey, is this data what we expected it to be? Or is this data incorrect and do we have to rebake it? Okay. So then we write the data to the file, and then, you know, we close it and stuff like this. You may want to do consistency checks here. It's like, you know, if you want to make this code more complicated, it's easy. But for now, I just want this code to be simple and to work. Okay, so then when we read the data, things are basically the inverse of what we have just done. But they are a little bit more to skip steps, actually. So let's keep things like this for now. Let's just do the saving portion. We are not running this function yet. We will do this in a second. Because let me just plug this in, and then I want to talk a little bit about loading. We're going to rework this format a couple times for sure, probably at least once in the stream. I just want things to work. So when we are specifying the scene mode, let's just immediately here yeah, let's just immediately here save the result to the cache. And this is going to be very redundant, obviously, because we just spent all this time, like, you know, talking about how we are trying to not do the thing, and then we do the thing, and then we immediately save the cache. But, you know, bear with me. So save it to the cache file, materials, draws, texture paths, camera, sun direction. And then if we failed the save, then I don't know, something is up. Okay, so let's run this. Oh, right, and then I have to add the file. I think I just have to rerun cmake. Okay, so then what should have happened is, let me increase the font a little bit, is that we got the cache file, which we did, which is a little bit larger, which makes sense. I'll talk a little bit about the size composition in a moment. But so we took this scene that's like, oh, we didn't save animations. Should we just save animations? The parallel arrays are annoying. Do we even play all of the animations? I need to look at the animation code. It's been a while. But like, okay, so we load roughly 100 megabyte file. Then we do a bunch of processing on this. We like generate levels of detail and stuff like this. And then we write out a 110 megabyte file. 110 megabytes is at the same time too little and too much. And I'll talk a little bit about why. But we wrote some code. The code saves some stuff to disk. Cool. Now we need to load this from disk. Let me look at chat. This is Zed. Yeah, so you can save the paths in a variety of ways. Using, you know, like 128 characters per path is not the only way to deal with this. It's reasonably pragmatic. You know, it's like, it's fine. But as I said, a bunch of this is going to be reworked in the future, so it kind of doesn't matter a whole lot. Okay. So when we load this from disk, what we could do is we could just write the exact inverse of this code. Meaning, you know, open the file, fread stuff from it, and stuff like this. Which we could do. Actually, maybe we should start with this, and then it's going to be instructive, because then we'll have to change it because it's not great. But let's actually write the stupid version, or the naive version first. So this is the exact inverse. We have the file, we open the file, we read if you want it to be nice when reading data from binary files, you have to do a bunch of checks. Like if you're reading something from a binary file, you have to check, did the file actually have that many bytes? Also, what if some of the data is just blatantly wrong, in the sense that, I don't know, what if some of these values are nonsensical and whatnot? I'm gonna ignore these concerns for now, because we are trying to quickly get to the point where we can look at the new profile and then, you know, do something about the profile, right? So we're just going to ignore the IO errors and whatever other nonsense can happen, because we're going to rewrite all of this code anyway in the future. All right, so let's do the sanity check that I was talking about. Oh, this is not great, actually. One thing I like to do, so I'm not, but we are rewriting all of this code anyway. Okay, anyway, I was gonna show a thing around file star APIs, but I decided whatever. So yeah, so we're gonna do basic validation, which is to say, if the file that we are loading is not like, does not conform to the requirements that we have in terms of the baking process, then we're just gonna pretend it's not there. But then otherwise we are going to just read everything back. And the way we are gonna do everything, the way we are gonna read everything back is basically just replace fwrite with a fread. But of course we need to allocate the buffers first. So let's do that. And then let's hope that all of this is boilerplate, so I don't feel bad about just using Copilot to, like, you know, do all of this nonsense. So we are gonna resize all of this stuff, and then we're gonna fread all of this stuff, and then materials and roll calls and texture paths and whatnot. And then we are reading the texture paths. We are reading the 128 bytes, and then, you know, hopefully it's null terminated, but if it's not, it's going to be a problem. So let's just say, and then I'll move 128 to a constant at some point, whatever. As you can tell, I don't care much about the structure of this code right now, because it doesn't matter. And then we are doing one fread at a time. We can, like, read the whole set of texture paths because it's now a fixed size. Doesn't matter. Let's just see if this code works, because it might. So what is the actual flow that we need here? The actual flow that we need here is that we need to try to load the SceneCache. Geometry, materials, draws, texture paths, cameras, sun direction. And then if we successfully loaded the SceneCache, then we are done. If we did not successfully load the SceneCache, then we need to actually, like, process the scene, save the cache, and then we are done. We might change this too in the future, but for now it's good enough. And then there's some other complications around some of the modes that we have. I won't go too much into these for now, but let's just say that I'm gonna do this, and then this fast mode thing is not great. We should like have removed it, but it's fine. Let's keep it. And then we'll keep CLRT for now. Okay, this is the main thing I wanted to change here probably. Okay, so let's just see, you know, what happens. We have a bunch of warnings and we have completely broken geometry, which serves us right. Oh yeah, ignoring return value of fread. Okay, great. Okay, cool. So the code did not work, obviously, because when we ran it just now, oh, actually the code did work. Okay, camera is off, because I didn't copy the camera from the header to the output. That makes sense. Okay, so the actual code almost worked. We need to fix, I guess just before we like return, we will update. If I remember correctly, there was also some funkiness, like the GLT file may have a camera or it may not have a camera, and here we are kind of pretending it always does. So ideally, we would save to the binary file whether it actually has it or not, if that makes sense. Storing bools is a little bit sketchy in binary files, but like it's fine. Whatever. There's also some padding questions that we will have to resolve at some point, but for now, just let's do a stupid thing. Yeah. Oh, but the problem is when we load the scene. Actually, yeah, okay, let's ignore this. That's fine, whatever. Our files have camera and send direction. Let's do this again, because this was just a loading thing. Okay, cool. So now these warnings are great, I guess. So the compiler really wants us to not do the shortcut that I was talking about, where, you know, I'm going to ignore the errors that may have happened during the reading. If I recall correctly, this is GCC. I think this doesn't even silence it. You really have to look at the value. Yeah, correct. Okay. I'm going to ignore this because we're going to remove fread from this code anyway. So let's just ignore this. So we have the code. The code worked. Let's profile it again and look at the result and talk about kind of the next steps, because this is not, we're not done. We are nowhere near done. But we have started. It's a good start. Okay, so this is the cached. Now, if we were to remove the cache file, obviously the loading would actually be slow, in the sense that we would do the whole thing that we were just doing there, where we like built the cache, right? And then we would save it to disk, which takes extra time, and then we will load it from disk. But saving it to disk and loading it from disk is not that bad, so it's probably fine. Okay. So now let's look at the resulting performance, and it's not great, and so we need to make it better, and making it better would involve more changes in the surrounding code and in the loading code and things like this. Okay. So probably the easiest way to look is the traditional view. One other important point about Superluminal. So I've been kind of switching back and forth between looking at the timeline and looking at the specific time information. And one important point here, and this is not unique to Superluminal, like, you know, the same thing you can do in Tracy. There's other profilers where you can do this, but even when you are using these aggregated views, where you just look at a function and say, oh, this takes this percent, this many percent, etc., it's like really convenient and really useful and really critical in some cases to be able to do this for just a section of your code. Now, in this case, it doesn't actually matter, because we could look at the entire profile of the entire application and just find the loadSceneCache call and then ask what takes time there. But there are cases where it's super important to not just analyze the whole aggregate run. Like, for example, here, if create buffer takes a lot of time in some places of our code, but little time in some other places, it may be useful to ask, what's the time distribution specifically for this call? And this is what happens when I click on loadSceneCache. It displays stats for just this sort of segment of time, if that makes sense. Okay, anyway, so If we look at loadSceneCache, now, well, the good news is it's way faster. It takes 50 milliseconds, which, if you recall, I was saying, okay, we have 2.5 seconds of work. Maybe we multi-threaded, maybe it's 10 times faster on 16 threads. So maybe it's 250 milliseconds. We're already like way faster than this, right? The best way to reduce the time the code takes is to stop running the code to begin with. So we have successfully done this. Good job. Now, the problem is if you look at the time it takes, it's still too slow. Why is it too slow? What is it doing? Well, it is doing vector append, which does memset, which does page faults and stuff like this. And then the actual fread takes some time, and then we have appends for a bunch of other vectors. So I want to talk a little bit about that aspect of the problem. Because my intention is not to leave the code like this, but I want to talk a little bit about what happens here. But other than that, nothing else exciting happens, right? So like the code runs, it's good. The other, let me actually fix the, one more thing that I will need. Yeah, so there's one other like complicating aspect to this, is that we have a couple of different modes in which we can build the asset data, and I didn't specify them. So if we look at this code, this code had like 3 Boolean parameters. I just hard-coded one of them to true. Fast mode is like not interesting really in this. Now we can just hard-code it to false. But there's this parameter that I kind of want to preserve. So what do these do? This parameter was basically saying we need to build meshlet data. There are cases where you're running on a GPU that doesn't support meshlets, in which case we previously weren't even building this data to begin with. Now we do. We could skip it, but if you have a dual GPU system and you build the cache for one GPU and you want to test it on another one, it's getting complicated. So, it's easier to just build the data, especially now that it's cached, right? And then fast mode was a special hack that we added at some point to make the processing of this data a little faster. It's not dramatically faster, so maybe we don't even need this now. Maybe we should remove it. But then there is this other thing. I forget if I didn't have a special stream for this, but there is this other thing that I've added at some point to work with NVIDIA's clustered ray tracing, which has a different way of building the clusters. And in theory, this is a thing that should invalidate the cache, because if you're building, basically, I think the general idea is this. If you're building the cache with the data for the certain hardware software configuration, you kind of have to like include this configuration in the cache header and then check that it's actually correct and expected. And if it's not, you have to rebuild the cache, because like, you have to build the data. So maybe for now, I'll just add the Boolean here, actually. And then, we will... there's like probably nicer ways to deal with this, but... You sort of don't have to have the padding manually, add the padding manually, but there's some quirks around initialization that I'll just ignore this for now. This code is not ideal in a way, but let's just ignore this for now. So I want to add this back. So essentially what this does is just, and then of course right now I changed the header. So the other issue with all of this is whenever you change the data, you kind of have to version the cache because you've changed the data format, right? And then that means the old file is there on disk, but it has a stale format, and you have to rebuild it because the format changed. And this stuff is easy to accidentally like get wrong in the sense that it's very easy. So just now I added a couple fields to the header. This breaks the cache. But you know, if I just run the code right now, something will break because the structure of the file on disk is not what we expect it to be. There's different ways to deal with this in general. I think one common way to deal with this is just add a version of the cache, and then you bump the version manually whenever something changes. I am gonna do. I'm just fine doing this. This is a good idea. So we can just, you know, like SceneCache version is 1, and then we'll just add a version here, and then if it's changing, like we need to rebuild the file. If it changed, we need to rebuild the file. But then the other thing I want, the other thing I'd like is just like maybe header size here, because I just want to not think about like changing the header maybe too much. Just, you know, you add some, although let's just add the version actually. And then people also like to add magic constants so that the first 4 bytes of the file are some specific, you know, thing. And then oh, very nice. I don't know what's a good 4-letter word. We can use cache because it's a common pun on this, but okay, let's do SceneCache or something like this, and then let's hope that the AI more is like good enough to just hallucinate the hexadecimal number. We will validate this in the file. Okay, so yeah, so for now we'll just do magic version, and we'll bump the version manually. There's other ways to deal with these sort of data integrity issues that are automatic. None of them are perfect in the sense that whenever you add a cache, you always will have a problem at some point where you forgot to do some validation thing, and then, you know, your cache is actually stale, and unfortunately it's difficult to sort of guarantee that the code that we have written is robust to various changes. Obviously, you could right now manufacture a cache file that has the correct header, but has completely garbled data after this, and that's not going to be caught, right? So you kind of have to accept some amount of imperfection in code like this. But you know, it's kind of what it is. If you're worried about the kind of integrity properties of this data, you could have a process where, for example, you like sign it cryptographically or something and then validate that signature. So there's ways to deal with this. We don't really care about sort of all of this. So, okay. Let's rerun the code. So right now we have to rebuild the cache because we just added the magic number and the version number and stuff like this. So right now it took a few seconds. If we rerun it, it's instant, right? Because the cache has been built. And then the thing I was talking about with the extra mode that I've just added is if I build the, if I run it with clustered ray tracing enabled, it rebuilt it because the header sort of didn't have the right thing. And then if I run it again in this mode, it's fast. And if I run it again in the default mode, then it's going to be slow, right? And then if I run it again, it's going to be fast. Okay, cool. So that's the general structure. We have the cache. We can invalidate the cache if something has changed, right? We can do it manually. We can add some extra stuff to the header to do this, etc., etc. Now let's go back to the profile and talk a little bit about kind of what we can do to fix it. Yeah, I was going to show a way to use the unique pointer with the file star to not have to close it, but then I figured I'm going to remove the file star, so whatever, who cares? So, right, okay, sure, let me talk about the, yeah, so you can add the hash, but then you have to like compute the hash and let's double check that the file is correctly prefixed. It is. So, you know, we have the magic number in the beginning of the file, which is ASCII for SceneCache. And then we have the version number, which is 1. And then we have a bunch of other header stuff. Okay, so let me just briefly talk about the align-s. Align-s is a good idea, possibly, anyway, but there is a caveat. So, okay, here's the caveat. So, if I remove this padding field, so I've added the padding field, I was doing this super quickly, so like if you aren't an expert on this, it may not be super obvious, but so I added a boolean. After this boolean, I added 3-byte padding. Why 3 bytes? Well, every other field in the structure is 4 bytes because we are using 32-bit integers. The camera is like a bunch of floats, probably. You know, let's actually check this. Yes, it's like a bunch of floats. And then the sun direction is obviously a float, 3 floats. If I didn't add the padding would have still been here because the compiler would have added it. Because when the compiler does the layout of the structure, in memory, it aligns every field to the alignment of that type of that field, which is 4 bytes for uint32. So the padding that I added here was always there, I just made it explicit. Now, the problem is if you don't have the padding, the bytes are there in memory and the bytes are there in the file. What are these bytes set to is the question. And the answer is, it's a little unclear. When we write the header to the file, I used this kind of shorthand when we just create a zero initialized version of the struct. However, when we say zero initialized, we may mean different things. The compiler means a specific thing, which is like the fields are set to their default values, in this case, not necessarily 0. There's complicated C++ rules. Let's not go into this. The critical portion is nobody promises you that the value of the implicit padding that is not explicitly like put there in the struct is actually initialized here. The correct way, sort of, to do this would be to just memset the whole thing to 0. And in this case, I can remove the padding and I'm guaranteed that it will be 0 because, you know, the memset put it here. However, that has a downside that the memset will, if there is any non-zero initialization kind of happening here, then it will overwrite this, of course. But, you know, it's good to do anyway, so let's do this. The same caveat could apply anywhere else in our data, really, in the sense that when we are writing, I don't know, like an array of mesh structures, everything here is 32-bit because like there's good reasons to do this anyway. But if there's ever a padding field inside of this struct, then the padding field might be left uninitialized. Do you care? So the answer to this is yes, in some specific configuration. So let's just talk a little bit about, so we are doing this in context of a render. That's just a GitHub project that you can clone and give it a GLT file and it's fine. But part of the reason why I wanted to do this is I wanted to show, like, as I was saying, like no actual game engine that, you know, you are using in production games loads GLTF files off disk, like on the user's computer. Like this is just a bad idea to do. You shouldn't do that. However, what also no engine does is ship the GLTF files and also like cache the loads in the way that we are doing right now. You always ship the final product. You always ship the cache in this case, right? You don't call it the cache necessarily, but you ship the cache. Now, let's say I ship you a file that has a bunch of binary data inside it, and some of this data hasn't been explicitly set to 0. If I run the code that builds the cache again from the same data, it might produce a result that is different from the previous one because it's like uninitialized data, right? So essentially, you could end up in a situation where uninitialized data ends in your final file that you ship to a user. This data doesn't matter in the sense that the code that runs on the user's computer will never look at the data, but the data is there. Do you care? Well, you might. The reason why you might is that it's a good property of systems like this that you can run them again and again on the same data, and they should produce the same result. If this doesn't happen, you could end up in a situation where, hypothetically speaking, you're preparing a patch for your game. You need to update the cache because you changed some assets. So you rebuild the cache for your game, and even the assets that never changed have a bunch of bytes flipped in the data of the assets. The patching system doesn't know that these bytes are unused by the code. It has to preserve the data, and so dutifully compresses and delivers all of these bytes to the user, and you end up with like, gigabytes of patches where the actual content change is like half of the patch, and the rest is like uninitialized garbage. It's not a big problem for headers per se, in the sense that the worst case here is we ship a couple extra bytes, but it's a good general practice to make sure you do not have uninitialized data in the output, in the binary output of your sort of serialization code. Anyway, but with a mem set, it should be fine to just remove the binary. So, okay. All right, so let's run this again. Okay, cool. So let's go back to the performance of the loading code. Actually, let me commit this. I like doing checkpoint commits. There's also some complications around object files, obj files, but we are gonna ignore them for now. This is fine as a good first step. And the basic scene cache, we now cache the the scene contents in the final optimized version on disk, and load the cache directly if we can. Okay. So okay, so then let's look at the performance of this code, and let's look at kind of what happens here, and let's think about, is there more stuff to improve here or not? It's a little unfortunate because there is the way this code is structured makes some things difficult to see because they're not like adjacent in the process. But okay, so all right. Okay, so let's look at what this code is doing, and let's discuss ways that we could improve on this. So what this code is doing is that it's resizing every vector, which takes like the bulk of the time, and then it's doing an fread into the vector from the cache. And the fread, as I discussed in the beginning of the stream, comes from the page cache. The terms are a little bit page cache is a very different concept from the cache that we just added. Page cache is the thing that takes the data from disk and then keeps it in memory in pages, which is where the term comes from, so that if you read from the file, the operating system, Linux in this case, but like every operating system does this, it can say, well, the data from this file at this offset is already cached in my page cache, in this page, so instead of doing a disk I/O operation, I'm going to just copy it. And so if you look at what the fread does, is this code inside the kernel where we do the syscall, we do fread, which gets into the kernel, does the syscall, then it does the ext4 file read, but instead of then doing the I/O scheduling, it's like, oh, I'm gonna copy the page to the output because the page cache somewhere in memory has this data, and you can just mem copy it directly into the process memory, right? The vector reallocation before this is doing a mem set. So the vector resize, which here is named default depend, but like don't worry about this, STL is funky about how they implement some operations. resize does a memset because the vector resize always keeps the result of the resulting vector like resized to the default value. It's not filled with uninitialized values. And so it's doing a memset. The memset by itself is kind of a pointless operation because we're just going to write the memory here anyway, right now with an fread. However, what actually happens as a byproduct of the memset is like what takes time in a memset is mostly not the memset itself. And you see all of these, so like we are doing a memset, but the memset calls SNX page fault, and then mm fault, and then all of the other stuff. So what actually happens here? So the unfortunate part about dealing with large amounts of data in your program, especially when this large amount of data manifests when you start the program, right? So we just started the program, it doesn't have any allocations, and then we allocated 100 megabytes of data, and then we read them from the file. This is what just happened, right? And this process took time. Oh, by the way, so the loadSceneCache takes 50 milliseconds, give or take. And using our trusty technique of not even napking, but like mental math. So as I was saying, the file is approximately 100. It's like 111 megabytes. Let's just call it 100 megabytes for to make the math easier. So it takes us 50 milliseconds to load 100 megabytes, which means that you need to multiply 50 milliseconds by 20 to get a second. Which means that it takes us, which means that it would take us a second to load a 2 gigabyte file, if the scaling works out. 2 gigabytes, a second to load a 2 gigabyte file is like 2 gigabytes a second. Is that good or bad? Well, I just said we aren't reading from the file, like the thing is in cache, right? Naively, you would expect that the time it takes to load a thing from the cache to your process is the speed at which you can copy memory from one place to another. On my system, you should be able to copy memory at, give or take, 20, 30, 40, let's call it 30 gigabytes a second. It's a little difficult to establish the exact number. There's like, the order of magnitude is wrong. The order of magnitude of the copying of memory on this machine should be like tens of gigabytes a second, not like single-digit gigabytes a second. So the question is why? And the answer is a little complicated, but unfortunately part of this is just we are only measuring 100 megabytes. If we had a gigabyte cache file, maybe we would have seen a faster number, like a smaller number. But part of the problem is just that it's expensive to manifest memory. It's expensive to allocate memory in large quantities, not because the allocation itself is slow, as in not because the malloc is slow. If you look at what happens during the vector as resize, it first has to do a malloc, and then it does a memset. But the malloc doesn't even show up in the profile. It's because the malloc itself is fine, because the malloc itself doesn't do a whole lot of work. It just establishes the address space that is not attached to any physical memory on Linux. Because Linux does overcommit. But when you memset, it has to page fault this memory, which means it has to actually associate every allocated page with physical memory. And that process is slow. It's not slow by, it's multiple gigabytes a second is fine, I guess, but it doesn't run at tens of gigabytes a second. So so this is not great. But my larger point is, I guess, it's not even technically the fault of StdVector in this case. Yes, StdVector is not the best container in the world and stuff like this, but if we didn't do the memset, maybe we would have seen the faster execution time. But unfortunately, it's likely that the code, if we were to remove StdVector from this and just manually allocate the memory, the code would still be roughly as slow or as fast, depending on how you look at this. It's a little difficult to test this theory, unfortunately, because there's no way, there's no official way to like resize the vector to the size without memset, and so it's a little bit non-trivial to like get a profile where, without rewriting the rest of the code that uses state vector, it's a little bit non-trivial to like actually remove the memset, right? I can try to just do this with the vertex data or something like this, although this would not be comprehensive. There's only 4. I think I can do this actually. I think it's fine. Okay. So this date is difficult. Yeah, okay. I think I can just do this with the bulk of the data. Okay. So don't do this at home. But what you could do is you could just replace resize with reserve. I think this should work. Let's test this, and then I'll comment on what actually happened. Well, this will not actually work. Wait, what? Oh, right. Hold on. This size has to be changed. Sorry. Geometry versus. Okay, so yeah, so this is gonna be a hack. But I think it will work, but it will not. I'm trying to I want to get a profile where I don't do the memset and things are just bad, to convince you that memset and the state vector is like not the problem per se. It's just a little bit annoying to do this. All right. So you can't actually do this seemingly. Actually, wait, what just happened? The process self-destructed. Do I use size for? Oh, because the code that copies data to the GPU uses the size too. Man, all right, this is annoying. This is annoying. Okay. I know how to hack this. I just don't. I'm second guessing as to whether I want to do this on stream or not. It's like a 9 to hack. This is the one part where if we didn't use STL, it would be very easy to actually test this theory. But because we use STL, it's much more difficult to test this theory. All right. Let me just look at this, and I guess I can just do this. It's fine. Hold on. This guy, start, finish, end of storage, and so we just need to patch finish to point to end of storage. Okay. So again, don't do this at home, kids. Template goes first. So where again? Hold on. Start, finish, so the okay. And then okay. Okay. I will explain. All right, so I removed the memset. Let's see. So the code now takes 40 milliseconds instead of 50 milliseconds. So it's like better, but it's not like better, right? It's not like, oh, it's now fast and it was slow. It's like, oh, it's a little bit faster now. It took previously 50 milliseconds, and the vector append operations that did the memset and stuff took like 75%. And so you would think, oh, I can replace the vector and the code will be 4 times faster because I don't have to do the work that the vector is doing. But that's not true. So what I just did is so the issue is the vector has a resize function that does two things. It resizes it allocates enough memory, and then it also initializes this memory. It's difficult to skip the initialization step. You can do it for your own types, but it's difficult to do this for primitive types. You can just reserve. What reserve does is it allocates the data, but then it doesn't fill it. But because we are just going to fill it anyway with fread right now, it's sort of wasted work to fill it. However, when you reserve, the size of the vector is still 0. The capacity of the vector, the allocated buffer, is large, but the number of elements that the vector tracks for you is still 0. And so all of the code that reads the vector size is like not behaving correctly. But of course, on the specific platform, on our current platform, we know that the vector is just 3 pointers. The beginning of the vector where the allocated data is, and then 2 pointers inside this storage. Finish is the pointer to the end of the actual data that is initialized, and then end of storage is the end of the actual allocated block. And so after reserve, finish is still the same as start, and then end of storage is the actual end of the actual buffer, and so we can just patch finish to be equal to end of storage, and that kind of resets the size of the vector to the correct value without spending the time to memset. However, as I was saying earlier, it doesn't actually save us the requisite amount of time, right? If we look at what actually happens now, we do an fread, it still goes to the same ext4 flow, then it copies the page to our memory. However, then when it actually does the copy, we see the same stuff that we've seen in memset here, right? So here in memset, where is the memset? Wait, hold on. Oh, this one is even worse. This one isn't even doing the memset. Oof. All right. So here we see the memset, and then we see the page fault, and then we see the page fault that goes into the fault, which is memory management fault, and then does memory management operations. If we go here, then this stuff is now under the copying code inside the kernel, right? So it does the page faults, and then it does these allocations for the virtual memory, for the physical memory and stuff like this. So basically, we had a bunch of code that inside the kernel allocated the memory actually for us as physical memory. And previously this code ran when we initialized this data with memset. But this has to happen, so even if you don't do the memset, it still happens just later when we do the reading from the cache. Anyway, okay. So the bottom line is this is still not super fast. So all of this is you shouldn't do it in production code, although it's probably safe if you actually get the layout right. But generally, obviously, don't use this. It's convenient to be able to confirm hypotheses, right? By writing code, even if you know this code is illegal by the C standard, by the C++ standard terms. But this doesn't even help us that much, right? Okay, sure, it's 10 milliseconds faster now, but this is not the main issue. The main issue is that the manifestation of this memory takes time. Okay. So we can fix that. However, I want to do another thing first. Because I kind of need this for some of my future experiments anyway. So I want to do another thing first. and it's going to be easier to show that that is useful if I do another profile without the page cache, or without like, yeah, the things being cached. Or maybe I should, let me, so disregard the experiment that we just performed, obviously, right? Because like, you know, things are still slow. I'm trying to think if I should, there's two more things I want to do ideally. So we're at almost 2 hours. Okay. There's two more things I want to do, and I'm trying to figure out if I want to do both of them or just one of them or what. Where is the, oh, I see, okay. Okay. Okay, I haven't really decided yet which one of them I want to do, but I just want to make one point. Even if I don't, it might be better actually for me to only do one of the things, because, okay. So okay, so like let's just go, let's just finish the thought, I guess. I want to sort of flesh out this thought process so that it's clear, but then maybe not write the code to fix it, because a similar problem exists in images, and you know, maybe we can do this like later, or like not next week, but like, I don't know, early next year, maybe next, on the next stream. But let me, oh, this is the wrong file. Let me, what does load image actually do? Right, load image is fancy. It bypasses this problem. It bypasses this problem. Okay. Okay. All right. So the problem here, right? The reason why this is still slow, quote unquote. I mean, 40 milliseconds is like pretty all right. But the reason why, but again, like if you were to, I really like, and I really highly recommend converting every possible performance number that you can find into like a speed of light measurement that you can ground in some way. Is 40 milliseconds too much or too little? Who knows, right? On one hand, it's way faster than 2.5 seconds that we started from. On the other hand, maybe it could be 10 milliseconds. Do you need it to be 10 milliseconds, or is 40 milliseconds fast enough, right? You could argue it's fast enough. So I like, from the perspective of figuring out not whether you need to make things faster, but whether you can, in theory, make things faster and how much faster, I really like grounding everything in speed of light measurements. So this is the thing I just did mentally, right, like a few minutes earlier. Okay, 40 milliseconds, 100 megabytes of data, this is this many gigabytes per second. This code has to copy data from one buffer to another. Wow, the actual copy performance should be way faster. So we are bottlenecked in other stuff, which is the kernel giving us actual real physical memory to use. And then the next question is, can we like not do that, right? But if, for example, we were copying here instead of like a megabyte of data, or instead of like 100 megabytes of data, if the cache was like a gigabyte, then I'd be like, okay, a gigabyte and 40 milliseconds, so 25 times that is a second, so that's 25 gigabytes a second. Wow, that's close to the memory speed, right? Maybe it's not like directly memory speed, maybe you can still make it a little bit faster, but it's within the right ballpark. And so, okay, like the way to make it faster would be to reduce the amount of data. So, but like then if we were to reduce this further, right, which actually we will not do today, but if you were to want to do that, then you need to ask, what do we do in a situation where the thing that takes time is the kernel giving us memory? And the issue is you could cache this in the sense that maybe we already have another buffer of 100 megabytes somewhere that we can reuse over and over again. But in this case, we are kind of loading the cache into the memory, and so we kind of need the memory, right? But you need to ask in these situations always what happens to that memory. So what does happen to that memory? Well, it's difficult to see on the profile because there is like all of this load image stuff that happens. But at some point after this, which is like basically this code, basically this, it's not like inside a function because it's just part of the like loading flow. But if you look at the code, we create like a bunch of buffers for this geometry, a bunch of Vulkan buffers for the geometry, and then we call the upload buffer function. And to the upload buffer function, we pass the actual like geometry data, right? What does it do? The first thing it does is it actually copies the data from the system memory that we provided it to another Vulkan buffer, which is called Scratch, which is also a system memory buffer. But it's mirrored into the Vulkan sort of addressable space. And so then we can schedule a GPU copy from that buffer to the final video RAM location. So what actually happens here sort of globally is inefficient because we take the file and then the file is in page cache, so there's some memory in page cache. Then we copy this into the newly allocated memory inside the process space. This takes time because, you know, memory management operations takes time. Then we copy this into the Scratch buffer because we need this in the Vulkan addressable memory. And then we schedule a GPU copy from the Scratch buffer into like, you know, the actual video memory, and then we wait for it. And this is what happens here, right? We copy it first, and then we schedule a GPU copy. Is this the vertex buffer, by the way? Is that the second thing that gets copied? No, this second to... This is probably the index buffer. Right, the index buffer right now in this code is very large because it's like using 32-bit indices, I think. I'm actually wondering how much memory that is, but the short story is maybe we shouldn't do this. The short story is we do a whole lot of work in various stages, right? But a lot of this work is kind of redundant because it's only necessary to prepare the next stage of what's about to happen. So we load into system memory, and then we copy from system memory to a Vulkan buffer, and then we schedule a GPU copy from the Vulkan buffer to the actual real buffer, and then we wait for it, right? And so that process takes like 10 milliseconds or so. And this first process took like 40 milliseconds after the vector hack. So together they take 50 milliseconds, but most of the actual work that's happening there is like pointless copying from like one buffer to another just for the memory to end up in its final destination. So what in these situations you can do, and you know what's like more optimal, is that you just directly copy from the page cache to the GPU memory. And there is a question as to whether you can do this. And the answer is sometimes. But I'm wondering if I should do this today or not, though, because to do that, it's not just a matter of me writing a little bit more code, because I have to reorganize some of the existing code. And I have to deal with the fact that I didn't fully complete this caching thing, because my code loads GLTF files, but there's also another code somewhere else that loads object files, which I think should still work, but it works differently a little bit, because you can still, so what you can do instead of loading the full scene is you can load an obj file, and then you see it stamps it like in random locations with random offsets. And what you can also do is you can like load 2 object files, and then they get randomly stamped in random places. And so there's no like there's no scene, right? It's just like a bunch of files, which is all fine, but to keep that working, I kind of need some of the existing code that's more difficult to remove with this cache approach. So yeah, I could write special case stuff. So I could change this code to like mmap the file, and then keep the pointers around or something. And then here, this is the part, by the way, where StatVector like does hurt us, because if we didn't use StatVector, if StatVector supported a functionality where you could transplant memory that you don't own into it without allocator hacks and stuff like this that I don't want to do right now, because I don't like C++ enough to like struggle with it. Then we could actually do direct mmap, and then this stuff would just work much better. Okay, so I'm not really sure how I want to rework this. So maybe the answer is I don't rework it for now. All right, maybe the answer is I don't rework it for now. So I wanted to show one more thing, and I kind of need this for some future stuff, or I need some support for it for some future stuff. So I guess I might as well do this. But for that, I need to do another profile with a page cache, I guess. So let's actually okay, so yeah, hold on, let's actually replace the loading internally with mmap, because I'll need it anyway in the future, so I might as well do this now. And then I can do the thing I wanted to do. And then this is going to be the stream. And then at some point next time, we can do further optimizations. Because essentially, okay, at this point, both for texture data and for geometry data, we are in a place where on disk, the data is in its final good format. And the only thing you have to do is copy that data to the GPU memory. And that copy takes time, right? Because of all of these intermediate buffers and like uploads and all of this stuff. So like it would be good to streamline that entire process. But that's a little bit tricky right now, because there's stuff I have to rework and things like this. So maybe I don't want to do this just yet. So let me do the other thing. But before I do the other thing, I just want to do the mmap, because it's a good thing to do, and it's going to set us up for the future stream. Okay. So the way we are loading the cache, the scene cache right now is we are just doing the usual file open, and then we are doing the fread, and then we are doing the fread and stuff like this. So this is all good and fine. However, in the eventual future, where we take the file and then we want to, as quickly as possible, load the file into the GPU memory, if the file is already in the page cache, this extra file like operation stuff is kind of getting in our way. And the classical way to deal with this problem is to use memory mapping. The other reason why this is kind of useful is the following. So we actually have a bunch of different arrays right now. And they're kind of all used right now in one way or the other, but I think eventually I'd like to move to not using some of them. For example, right now we have an index buffer. This is a traditional index buffer for every mesh that you can just use to render stuff. And we even keep it for every level of detail. So there's like many of them, many of them. But we also have meshlet data, which again you could use to render the thing with mesh shaders. And the reason, part of the reason why we do this is that you can just switch between these two modes. So if I run the code right now, it's using mesh shaders. I can press a button, it stops using mesh shaders. You know, like on this scene, it doesn't matter what you do because there's little geometry comparatively, but in some other cases, it does matter what you do. And then we do ray tracing, which again needs some of the index buffers to build acceleration structures. We don't need this for levels of detail. So there's kind of a mishmash of things that you may or may not have to use in different circumstances. It would be nice to remove some of these at some point, but also if we don't remove it, it would be nice to not load a thing if we don't need it. But the current structure of there is a bunch of vectors and there's a file makes it more difficult to do so. So for all of this stuff, it's usually much nicer if you can use mmap. So what mmap is just instead of loading the file with file operations, you have a special syscall that gives you that file as a portion of your address space in your process, and then you can just read bytes from that address, and then you get, you know, values. It's not always faster to use mmap. It's a little bit complicated. But mmap unlocks a bunch of things that are just much more difficult and annoying to do if you don't have mmap. So, you know, I think in these circumstances, using mmap is probably a good idea. And we might want to do the same thing for textures, but maybe not. I haven't decided yet. For now, let me just write all of the code here. But then we can still do the same slow thing of like allocating vectors and then copying data from two vectors. It's just, again, like we do everything in small steps, right? So the small step is adding mmap code. There's no standard way to do memory mapping. There is two that you have to do, basically. One set of APIs exists for Windows, and then one set of APIs exists for Linux. I can write the thing for Linux, but I can't easily write and test the thing for Windows here because it's a Linux system. I had a thing, I did this for my blog post that I already linked earlier in the stream. Let me look at this code and then see if I can just steal some of it and then like rework. Yeah. And then it returns pointer and size, and then you can unmap the pointer and the ref counts and stuff. Okay. Let me unapologetically, normally on the stream we write code instead of stealing code, but I'm not gonna like, you know, let's put it in a separate source file, just so that if we do need it for textures in the future, we can use it. Okay. All right, so and then we might want to add some other file utilities. One thing I talked about but didn't actually do is what you could do is you can check if the modification time on the cache is earlier than the modification time of the file that you're loading, and use it as an indicator that you have to refresh the cache too. We don't really need it, so like I won't bother. But there's other file IO stuff that we might want to do in the future. Okay, so and I wrote all of this code in the context of a project that had to parse very large GLTF files. And this, so I have a bunch of mmap code that's like, as you can see, specific to the use of memory mapping in context of a GLTF library. But here I just want to do like an abstract thing. So given the path, I want to memmap a file, and then it returns the size of the memory mapping, and then it will return like null if it can't or something. And then you can unmap the file by giving it the same arguments. And if you've worked with memory mapping in the past, there is a more often you see people sort of opening the file and keeping track of the ID of the file, of the file handle basically, so that you can close it later. On both Windows and POSIX systems, you don't actually have to do this. You can just like close the file, and if there's a memory mapping open, it keeps the file mapping like valid, I believe. So and that makes it easier because you don't have to keep track of like a whole extra uint or int or handle object or whatever. Not that it matters a whole lot, but just pointing that out. Okay, so and I have to change the Windows code kind of blindly because, like, again, I can't compile for Windows right now. But let's do the non-Windows thing first. So the way this works is you open the file, and then you ask the file how big it is, because that's what you do. And then you can't actually memmap empty files. Well, I mean, an empty file is empty, so there's nothing to memmap, I guess, right? The mapping call will fail. But we don't really care, right? So I guess I can just do or the size is 0. Depending on when you need mapping, you might have to handle this case in a special way, but yeah, but we don't really care. We don't need to handle empty files. Okay, so then you call the special mmap syscall, which maps the file into your address space. You can map files in a read-write fashion, but we only need this for reading, so we'll just do this for now. Okay, and then once we did do this, then we report the size and we return the mapped pointer. All right, and then to unmap, you just unmap. Okay, so this is the non-Windows portion. The Windows portion is the same flow, but just like all of the APIs are different, and it's kind of impossible to do this without being able to test on Windows. So okay. So I'll try to blindly make this work, but maybe this code won't compile or something, I'm not sure. So similarly, I don't even get IntelliSense because this code is disabled. Okay. Interesting. Okay. So then we try to create the file mapping object, and then we actually map it, and then we can close both the mapping handle and the actual file handle. And the view, the kernel basically should keep track of the association via the actual like file handle, file by the map pointer, and the same thing happens on Linux. And that's convenient because you don't have to. It's especially convenient for cross-platform interfaces because on Linux, if you were to preserve all of the handles true, then on Linux you only have to preserve the integer one, and then on Windows there is like these two handles that you have to keep track of. But turns out you have to keep track of like none of the above. So that's very nice. And then this is a size T. Right, there's a minor issue in memory mapping in either case. If you are trying to map a file that's like larger than your address space, then this should not be possible. But if you try to map a file that's like 15 gigabytes on a 32-bit system, then you have to have extra checks here. But like we can do like this. And then we can do the same thing here. This is kind of redundant, but just to like avoid surprises. I don't remember where size max is. Can Clang fix it for me? The answer is no. Student. Okay, really? That's surprising. Is it in std_def? Because size T is in std_def, so surely size max. Okay, weird. All right, and then I don't need this. Then I need all of this. Okay. Okay. So then on Windows we return the size, and then we return the pointer. And then when we unmap the thing, then, we unmap the thing. Oh, you don't need the size, right? So you don't need the size for Windows when you unmap, but you do need the size for Linux when you unmap. Okay. All right, so let's build this thing. All right. And now we can just use the resulting functions instead of file open, file read, and it should be roughly the same thing in our current circumstance from the performance perspective, but it will make a bunch of things easier in the future, hopefully. So let's file saveSceneCache. Path, file size. If we didn't load it, then we failed. The one thing that gets tricky in mmap files is a variety of file I/O errors. Get kind of weird to talk about. So like you open a file, you get a pointer back. You can just read from this pointer. Cool. But what happens if that read triggers an error, like a disk controller returns an error? Bad things happen. As in, like, on Windows it's an exception. I'm assuming there's some sort of signal or like whatever that's raised on Linux. And it's really, really difficult to handle. Sort of the concept of the memory mapping files by its nature says you forget the fact that there's a file and you just access it as memory. But with memory, there is not really a notion of legitimate failure when accessing memory. You just assume your hardware is like completely broken if a memory read fails, right? You can have ECC memory that can fail to correct some of the errors, maybe, but in this case, kind of your system is hosed, like you can't handle the error. So in that sense, memory map files are a little bit awkward. And also they get a little bit awkward when we talk about out of bounds reads. So what happens if the file is 5 bytes? Well, you can map the file, it will get 5 bytes, well, it will get a page. But then what happens if you try to copy a megabyte out of this file into somewhere else? Well, there's no megabyte in that file. In the non-mem-mapped version, the read operation would fail. In the mem-mapped version, the copy would copy data from after the mem-mapped region, which is potentially a problem. So you kind of have to trust the data, and we trust our data to like a limited degree. So, you know, hopefully, like, how do I put this? I think given the fact that we don't do deep validation of the data in the file, we aren't really changing the security properties such as they are of our code. Did I call it unmap? Let me just call this map and unmap, I guess. I don't know. mmap and unmap. All right, fine. Let's just do unmap file is such a weird name. Let's just do unmap file. Yeah, so hopefully that makes sense. And when you're dealing with like untrusted data, basically, then mmap files get a little bit quirky because it's easy to forget about the fact that the memory that you have is like not, you know, not trusted. Whereas with file IO, it's a little bit, okay, I do an fread. Oh, an fread might fail. Oh, it's an fread. Clearly the contents is not trustworthy. All right, and then the other thing, of course, with memmap files is that you don't have, when you have a file object, there is a concept of the position in the file object. When you have a memmap file, you literally just get a buffer. I'll do like a small helper for this stuff. Just to make it easier a little bit to work with this code. So we are gonna, what we were passing? So we are passing the data to copy from, or to copy to, and then we pass the size. I guess it's just going to be, it's fine. Says t size, says t count, and then file memory, and then file offset, and then we'll just blindly trust the data. There's like other fun things that can happen. For example, we have these counts in the file, and when you multiply count by size of an element, this multiplication sometimes can overflow. So there's all sorts of fun problems with untrustworthy data, which we will not handle at all. So, you know. Okay. I just try to match the interface to a fread so that it's easier to change this code. Okay, and then instead of close, we do unmap file size. Okay, hopefully this works. All right, see, this worked. Now let's profile this. It's probably roughly the same for 50 milliseconds or whatever, because like, but this is not why I'm doing this, right? I'm not doing this to make things faster right now. I'm doing this so that in the future some other things are easier to do. So we actually, it's like a little faster than our original state vector version. It's 44 milliseconds instead of 50. We could do the horrible hack again with the unsafe resize, which is fun, I guess. well, okay, fine. Let me replicate this. So we do vectors reserve size, and then we do, and then we do this, and then we do this. The thing with these vectors is like most of them are small enough in terms of the number of bytes, so all of the memory like operations being expensive stuff I was talking about doesn't really like matter that much. It's fine. It's like it doesn't register on the profile, but for some of these the buffers are like large, and so you know you have to be aware of the cost. All right, I will not actually commit this unsafe thing, but it's just interesting to look at. Okay, yeah, so this is roughly the same. So it's like 40, doesn't actually make things better. 44, 47. The other thing I should have mentioned at the beginning is when you start looking at these run-to-run differences, especially around file I/O and memory mapping, there is a fair amount of noise in the measurements, more so than you would usually expect. And so whenever we see, okay, like 44 milliseconds in one run and like 47 milliseconds in another run, oh, surely it's slower. Maybe it's not slower. Maybe it's the same actual cost. But yeah, so with mmap, it doesn't even matter. Our unsafe thing saves us like no time, because the actual cost, as we were discussing, right, is in the kernel mapping operations and the actual copy, but the actual copy is fast. So, okay, let me run this again without the unsafe hack, because this is actually, the code with the mmap is actually reasonable. So now, right, we didn't make things faster, but these will allow us in the future to do certain things better. And in particular, it should allow us to do one thing right now, and that is cool. 10 milliseconds to do the actual copy. So right, so the actual copy takes 10 milliseconds for like 100 megs of data or whatever, which is roughly speaking 10 gigabytes a second. 10 gigabytes a second for mmove is acceptable at these small sizes, I would say, sort of. It's like slower than what memory copies should be running at, like 2 times slower or whatever. It's closer ballpark wise, and you always run a risk of like I need to think about, you know, how to measure this accurately to say, can it be faster or not? Like it's a little bit, it gets tricky. Once you're like copying memory at like 10, 15 gigabytes a second, it gets a little bit nuanced to get to the peak performance of the copy in certain cases. Like it's very possible that it's, that you can only reach this rough number on a single thread, for example, and so you could copy on like 5 threads, but you know that's probably at this point irrelevant. Okay, so why did we do all this? So first, it prepares us for the glorious future that will not happen this stream. Second, it allows us to do one cool tweak that I just want to have in the code. So I'm gonna do that, but first I'm gonna look at the chat. Pre-allocating and using arenas or something would be faster in vectors. Yes, but so it's like the problem that we are facing here is that we have an app, it starts up, it loads a 100 megabyte file into memory, and then, you know, other things happen. In this circumstance, when you're optimizing this initial load, and at the scale of 100 megabytes, honestly, who cares? Like, yes, it takes an extra 30 milliseconds to map, you know, 30 megabytes, who cares? But it may matter once you go into the gigabytes range. It was a significant problem on some operating systems, at least on the thing I was talking about in my blog post that I referred to earlier in this blog post, because there the data scale is like tens of gigabytes. tens of gigabytes of data, like mapping that is an ordeal. And then there's questions about there's questions about multi-threading and stuff like this. But yeah, so I think the general statement is this. It's difficult to remove the kind of original, when your process starts up, your process needs X gigabytes of memory. It's difficult to remove the problem for these original X gigabytes of memory, because like you need the memory. But if you can not need the memory, which in this case I think in the future will be true, we are loading data into system memory, but we are just doing this so that we can copy it later to Vulkan buffers. We don't really need that, right? So if we can A, not need this memory, or B, if you can reuse the allocated memory over and over again, which is your point about arenas, right? Then it will like definitely be faster, because this is a one-time cost per freshly allocated memory buffers. For example, if you're processing like 50 gigabytes of data, but you can process this 1 gigabyte at a time, then allocating 1 gigabyte and working within that 1 gigabyte will be way faster than allocating 50 gigabytes and then working, you know, within the 50 gigabyte data. Not because of like caches or not because of like complex marker architectural stuff, but just because you have to page fault all of the memory that you're using into the process, and that takes time. So on modern operating systems, doing this stuff over multiple threads actually does scale okay, reasonably well. So, you know, the other thing you should do when you have 50 gigabytes of data is not use one thread, but that's besides the point. Yeah, why am I writing Win32 code on Linux? So this project works on Windows. I just want to not commit the code that I know will not compile on Windows. So I wrote code that I think probably will compile on Windows. But yeah, I'll test it at some point later. Outsize equals 0 is what the null should be. This is presumably talking about the mapping code. Oh, oops. Thank you. Does it matter if you map the whole file or sections of the file as I read through it? The auth should only page what is needed, or at least print it. Yeah, it doesn't. Like, I wouldn't stress about not mapping the whole file if you need sections in the modern day and age. You do need address space. So again, if you have a 100 gigabyte file, you need 100 gigabytes of address space. However, operating systems generally are pretty well optimized for sort of reserving the address space. The issues that I'm talking about with address space are only because we actually access that, right? If you can mmap or allocate or whatever, like terabytes of address space, and it's reasonably fast, it's like fine. Now, if you wanted to read terabytes of memory, now you're start interfacing with the memory management code that does page faults and stuff like this. But it's not, the problem is not the amount of address space. The problem is the amount of address space that we actually end up accessing. Now, if you have a 32-bit system, you have a problem. You don't have terabytes or gigabytes of address space, right? So I think in general, in 32-bit systems, mmap is a little bit dicey, because if you only need sections of the file, if I give you 10 gigabytes of data on a 32-bit process, for a 32-bit process, you can't mmap it in one go, so you have to do it in chunks. So that becomes a little bit less interesting. But on 64-bit, it's like a nice way to do stuff. So the sequential hints are a little complicated on Linux. Unfortunately, the one downside of using mmap is that you can't control the I/O operations very well. And because of this, you're kind of at the mercy of what the kernel does. I looked into this at some point last year, I think. Yeah, early last year, I looked into this extensively because I was working with like multi-gigabyte files for machine learning stuff. And it was not, so a sequential hint exists. It helps read large files quickly. All of this is not super relevant when the file is in page cache. When the file is cold loaded from disk, there is some stuff that you have to do to make mmap faster on SSDs, and it's still difficult to get to the peak performance of SSDs without reading many files in parallel. But also, or many, without reading the data in parallel, it can be one file. I think in general on SSDs, my understanding, my vague understanding is on SSDs, if you can do many requests in parallel, you kind of should, it will be faster. And so with mmap, if you can read the data from multiple threads, it's actually pretty good on SSDs, because it will read like individual chunks in parallel and stuff like this. But yeah, there's other stuff around mmap, like there's hints, there's sequential call. When I say hints, I think there's like there's mprotect stuff. There's some other things around mmap that can be used to optimize it, but we're not gonna like do all that right now. So let me commit this and then do the final thing that I actually wanted to do, which is almost the reason why I added mmap. Add memory mapping for SceneCache loads is approximately the same speed of loading the data right now. However, in the future, this may help us optimize things in various ways. So yeah, you don't have to use mmap. It's absolutely not a requirement. And in general, the file I/O is a difficult topic, is a complicated topic, because there's a bunch of different approaches. They all have different trade-offs. Some of them are fast in one way, some of them are slow in another way. It's like stuff like this. I generally like mmap, but it's not a panacea for a number of reasons, unfortunately. Okay, so the final thing I wanted to do is I wanted to do a little bit of compressing this data. And it will kind of be a little bit counterproductive in the sense that the way we set things up right now, when you load the data from the cache and it's cached in memory, it's very fast. It's mostly just copying data, right? So we have all of this like memory reservation stuff, but the full load is like very short, and so probably by adding compression we'll actually make it a little bit slower. However, you know, it's for the good cause, because the like in the future when we load things directly into the GPU memory, things will be better and stuff like this. So anyway, I just wanted to do a little bit of compression. Maybe optionally, actually. Let me do this as an optional thing, because now with the way we set things up, it's actually super easy to add things, and then as like you know, if you want to enable it, you enable it, and then we can keep both paths around and stuff like this. So okay, that's actually going to be fine. And specifically, so somebody was pointing out that I can use LZ4 or whatever to compress the data. Let me talk a little bit about this. 2:37, 20 minutes. Okay, that's fine. Let me spend a little bit of time talking about this, and then a little bit of time writing code, and then we'll like end the stream. So we ended up with oh, I can actually, okay, actually, now that we have the cache on disk, some things are easier to show. Okay, so we have the cache. We have like 2 GLTF scenes, and I was using them interchangeably. Oh, we didn't save animations in the cache, but like whatever. Animations are going to be broken when you use the cache. It's fine. I'll fix it later. So there is a cache on disk. The cache is like 100 megabytes right now. The composition of the cache is there is a bunch of vertex data. So I mean, we can look at this. Oh, and in fact, we can. All right, let's do a little bit of as I'm talking a bit about this, let me do a little bit of like I'll add some code that can like dump things and whatever, like print the sizes of things and whatnot. So the cache composition is there is vertex data, index data, and then meshlet data, and then a bunch of like small things like mesh headers and material headers and whatnot. The bulk of the data is vertex data, index data, meshlet data, and then we also hacked a bunch of stuff for ray tracing, or maybe I did this off stream, I don't remember. There's like some duplication of some of the stuff that's gonna be good to remove at some point, but there's a bunch of data on disk. And it's just a bunch of binary data, right? So when we load the thing from the cache, when the cache file is cached in memory by the kernel, then the fastest thing to do would be to just copy it out of it, memcopy, right? Because any compression that you do will not run at the memory speed of copying the data. And the it's like whatever you do, it's gonna decompress slower than memcopy does it, even LZ4, and then your end result is gonna be slower. However, it may still be worth it to compress the data. Why? So the first, so I mean, if you're shipping this file to your users, then obviously smaller files are better, right? So you may want to compress just for the sake of the file being smaller, and then take the hit of decompressing it off disk. I heard people don't like multi-hundred gigabyte game installations, right? So like you might just want to compress because it saves you space on disk. That's straightforward. However, the other thing is you may want to compress because it saves you time. When does it save you time? So if the file is loaded from disk, not from the cache, so if I purge the cache, the memory cache, and then load it, then we have to actually load the bytes from disk. And then if we discussed at the very beginning of the stream, okay, like SSDs, a couple of gigabytes a second. If you just do an FRead, it's just a gigabyte a second on my system because there is some complications around SSD loading and performance and stuff like this. 1 gigabyte a second is not that scary because a compressor can decompress faster than this in certain cases. And so we could save time just because when the file is loaded from disk, and to be clear, when the file is cached in memory, that's like a case that is helpful for me when I'm testing the code because I keep running it off the same data. But if you're actually shipping a game, you know, you probably are not reading the same data from disk multiple times. So the data not being in memory is the baseline case, actually. It's not the it's not the case that we'd expect to hit that often in practice and production. And then the second thing is, even if you do rely on the in-memory cache, compressed data takes less space in the in-memory cache. And so, you know, the smaller the data is, the more space there is for stuff in the cache. So in general, compression is good. However, you have this complicated, delicate balance. Okay, I compress it, I have to decompress it, that takes time. For example, if you can't decompress at 1 gigabyte a second, then you're running off a reasonable SSD, then the only good part about kind of adding it is saving space on the user's PC, or maybe saving download size or something like this, right? Because you aren't making things faster, like your decompressor is too slow. If your decompressor is like 3-4 gigabytes a second, okay, we have stuff to talk about. All right, so let me, I was gonna actually add some prints. So because of this, there is always this question when you're adding decompression with a specific technique, there's always this question of, okay, how much does it compress? But also how quickly can I decompress it? There's cases where compression time is important, but it's kind of more like less common. Because of this, it's difficult to say, oh, always use this compression algorithm. It's going to be good for you. Because, you know, who knows? Some compression algorithms may not compress the data that well. Some compression algorithms may not maybe too slow to decompress. There's always like this complicated balance. So anyway, the reason why I'm telling you all this is so let me just, I added the verbose mode. Let me add just like some prints. And then there's this meshlet RT data essentially, which is meshlet VTX0, and then everything else I'm just gonna ignore because it's not that big. So let's look at the what did I do? Okay, so now let's look at the SceneCache. So now at some point I'll probably add the command line argument to like, yeah, I will not do it right now, but it can be useful to just have a way to always rebuild the cache, of course, right? But for now we'll just do bistro GLTF cache, niagara bistro GLTF. Oh, this is without the verbose mode. Let's do this again, but with verbose mode. Okay, so so we have 26 megabytes of vertex data, 46 megabytes of index data. We never, this is using 32-bit indices, so it's actually around 23 megabytes of useful data, and then most of the rest is not useful because the indices are too large. We never like optimize this because meshlet data was the more interesting thing to use. So meshlet data is reasonable. It's like 23 megabytes. It's about as large as what the index buffers would have been if they were 16-bit. You can like optimize this a little bit further. And then there's also 14 megabytes of like extra data for ray tracing. That's only useful if you have the NVIDIA's ray tracing thing enabled, I think. Which is a great candidate now for not loading from the file, for example, right, if we don't need it. But I won't bother with this for now. So there is an interesting question, which is, okay, so we have this cache file. So I talked about the differences between different compression algorithms. I'm actually not sure, so let's see. So I think I have LZ4 and the standard installed. With both compressors, you can point them at a file and ask them to benchmark it, which means it will compress it and then decompress it and then measure the decompression time. So I have no idea what the numbers are going to be, so let's look at this a little bit. Okay, so LZ4 compresses the file. You can also trigger higher compression, which is going to be slow. I don't remember how. 12. Why 12? Okay, 1.8. Okay, let's just use the baseline version. Yeah, okay. So we could compress this file using LZ4, and then the result will be approximately 1.5x smaller, and then it will decompress it at around 4 gigabytes a second. So that's pretty good, right? This is probably worth doing, because unless you're running on a system where you can actually get more than 4 gigabytes from SSD of read speed, which can be difficult. We get 1 right now, so like for us it's worth doing. Then LZ4 will probably save you time, right? Because the file will be smaller on disk, so you'll load it, you'll decompress it, etc. You can also decompress on multiple threads, which will be proportionally faster. But the compression rate is only 1.5x. And then you can ask, we have these different, I mentioned 4 types of data. It's a little bit annoying to measure the compression rate for each one of them, right? So like, I don't know what to what extent maybe LZ4 is great at compressing one specific buffer out of these 4, but much worse at compressing some other buffers. It's hard to tell. So we can ask the same question for the standard. The standard has more levels of compression, so we can test more of them, but like whatever, let's just ignore them and just this one. So the good news for the standard is it will compress the file much better. It will compress at 2.6x. However, the bad news is for the standard, it will decompress at 1.4 gigabytes a second. Now, it still may be worth doing, but things are complicated. Because, okay, so on our SSD is pretty good. We, even with suboptimal I/O operations, whatever happens in the kernel, we don't know yet, but we are getting 1 gigabyte a second. This standard compresses 2.5x. This is like too close for comfort, because if you're using one core to decompress the standard data, then you can like overlap. So with memory mapping, what you can do is you can run decompression code, and the operating system kernel will try to prefetch pages ahead of where you're reading them. And so in theory, the reading from disk may overlap the computation, which is why mmap is occasionally very, very helpful. So there are cases where even though the decompression rate is like kind of close to the raw read speed, it's still a good idea to do, but it's kind of too close. Like, you know, it's like maybe this is a good idea, maybe this is a bad idea. It's really hard to know. But these are kind of the things that you should be thinking about when selecting the compression algorithm. Now, the thing we are going to do, obviously, is neither of that, because, you know, I'm not going to like integrate the standard LZ4 here. The thing we're going to do is Mesh Optimizer has a couple of good compression algorithms that are really good for specifically, or pretty good, specifically for vertex data and index data. I don't have anything for meshlets right now. And this meshlet RT stuff is basically a vertex buffer, actually. So I could actually compress that using the vertex data compression. So out of these 3, there's nothing, I don't have a great answer for meshlet data right now. But I could just compress vertex index and these RT data, like using a few lines of code. And, you know, the end result will be the files will be smaller, and the yeah, I guess that's it, right? The files will be smaller, and then if you're reading them from disk, the result should be that the file is smaller, so the I/O cost is reduced, and if the decompression is still fast enough, then, you know, you can still get the time benefit. Now, unfortunately, I don't have like a command line thing that I can just run right now and give you the same data, right? And in fact, part of the problem for even these numbers, as I was saying it, okay, this is the bulk of this file is 4 buffers. And these buffers are dramatically different in what data they contain internally. And so these numbers are kind of meaningless. The decompression performance tends to be close-ish, depending on the type of data. But the compression ratio is completely off the place, like all over the place between these 4 data types, probably, right? I can split them into multiple files, but we are already almost 3 hours in the stream. So to do this to just get the accurate estimate of the compression rate, I don't want to do this. The one thing I can do, though, is I can try to remove the meshlet stuff from consideration to begin with. And then just see how the compression ratios change. This is easy to do. I can just restore this thing, mesh shading supported. It's a little bit of a hack, so I'm not gonna like commit this, but so I'm gonna regenerate the cache. Oh, sorry, actually this way. I'm gonna regenerate the cache without meshlet data. Something might explode. Yeah, things exploded because my cache now doesn't have meshlet data, but my code assumes it does. So obviously it's a quick and dirty experiment. but we can now repeat the benchmarking thing. Okay. So Z standard, so the rate of overall compression in Z standard increased a little bit. And then, but LZ4 is almost the same, like 1.6 instead of 1.5. So just vertex plus index data, not in account, not like if you don't compress the meshlet data, just vertex plus index data in aggregate would compress around 3x with Z standard and around 1.6x with LZ4. I don't actually know off the top of my head what will happen with my compressors, but let's see. But it should be pretty good. It should be basically my expectations are it should be close to the standard, but maybe not. I think it should be close to the standard, but it should decode at LZ4 speeds, roughly speaking, in this case. So. Okay, so how do you do this? It's quite simple. There is complicated data preparation steps around the compressors that exist in Mesh Optimizer. However, our entire pipeline is already using all of this. The details are like in the docs. So we don't have to invent anything new. We just have to we don't have to change anything else in the code because everything else is already prepared in the optimal fashion. We just have to add support for it and just compress and decompress the data. So to do that, I'll add a compressed boolean because I want to have a way to enable it and disable it. So when you save the SceneCache, okay, and then I guess these Boolean variables are getting out of hand at some point. You know, I should refactor this, but okay. So let's just add this. So when you save, you should be able to say, I want compressed or I don't want compressed. And then we'll save that fact into the header so that we know if we need to decompress or not. That seems straightforward. But then the other thing we need to do is when we are using compression, we need the number of bytes in the compressed sections in addition to just the counts of things. And so we'll say vertex compressed vertex bytes. And then, as I mentioned, we can compress index data too. And we should be able to compress this like weird vertex 0 thing. Do I need to? I kind of want to for complicated reasons that I'm not going to explain. So let me just do that. So, okay. And then we will leave the meshlet data uncompressed for now. Okay. So these are 0 by default. And then, oh, we are writing meshlets. Let me also change the thing a little bit. Hold on. I mean, it doesn't really matter. The order is a little weird in this file, which is fine. At some point, we'll come back to this. Okay, so now if compression is enabled, then instead of writing the original data, we need to do something else. Maybe I should add a helper for this, actually. So, so I want to give it the original data, vertices, stride, count, and then the file. All of the like details are obviously in the documentation of the library, so I'm not gonna explain that. I do need the header to vertex bound. This compression is used in like many projects. Valve uses it for stuff. Legend of Zelda uses it for stuff. I don't know. GLT Files uses it for stuff. It's used. It's pretty good. So the way compression works is you say, hey, I have data, I want to compress it. It tells you how. Right. The reason why I don't get IntelliSense is I'm not including the library header. That makes sense. So it tells you the maximum number of bytes, and then you call the function. And then it has a couple levels, but really there is one main level that's useful. And then you give it the buffer, you give it the size, you give it the source buffer, count, stride, and then you write the results. Okay, that is it. And then obviously you have to decompress it, but. And then the index data is the same thing, but the index data, let me call it like right triangles compressed. It's fine. I'll call it like right index compressed, but there's two different compressors, one for triangle index buffers, which is good. And then there's one for like random index buffers, which is less good. And obviously if you have triangles, you should use the good one, not the less good one. All right, so you just do index buffer. Okay, code verse. All right, so the index data is typed, of course. So there's no stride, there's just indices. Right. And then the index data compression is a little bit funky. Why do you have to? Oh. All right, interesting. I think this should be fine. Things are a little bit interesting in this kind of setup. The different part of this code is that typically you use these in your mesh code, and so you have the mesh and you're compressing the mesh. Here we don't have the mesh. All of the meshes have been like aggregated into these giant blobs of data, and so we kind of lost the track of where the meshes are, and so we don't have some of the information available, but it shouldn't matter. Oh, right, it only matters for the... I should have like a separate function. I'll add this in my to-do list. Vertex count could be optional somehow. Because in our case, we basically just don't know what the maximum value of the indices is. We could compute it, but anyway, whatever. This API was designed for a slightly... for like an adjacent use case, but it should work. Okay, so then we encode it and then we write it out, and then when we part of the reason now, or like why did I do the mmap thing? Well, now that we have memory mapped file, the compressed data is in the memory mapped file, and so we can literally just call, instead of memcopy from the memmap file, we can call decompress from the memmap file, so we don't have to do any extra work other than the like decompression. You know, we don't have to allocate extra buffers and things like this during the decompression, which is very nice. Okay, so the one thing is we need to return the number of bytes that we have just written so that we can store this in the header. Okay, so now if we are using compression, then we, instead of just Oh, and of course the issue with this flow, which is fine, is we write the header and then we write a bunch of data. But if we are compressing this data as we are writing it, then we need to actually save the number of bytes into the header. Okay, that's fine. I'll just hack it right now. So compressed vertex bytes is write vertex compressed, and then the rest of the arguments is the same. And then here it's the same thing, but it's index bytes. And then it's indices data, and then you don't have size off, and then it's indices size. And then I think you should be able to, so meshlet data, like we just write uncompressed. I think you should be able to compress this thing as a vertex buffer, because it's essentially a vertex buffer. It's like at some point when I was doing ray tracing, I added some cache of some like vertex data formatted in like a special way to accelerate some operation. All right. And it's always 4 16-bit unsigned integers in a row. So that's how the vertex structure there is laid out. Okay, so I think this is right. I'm not sure. We'll see. You know, we can save the cache, but can we load the cache is the question. So then, as I was mentioning, oh wait, compressed meshlet vertex. Right. Okay, so then as I was saying, we like have already written the header to the file, and now we are changing it. I could change the structure of this code, but instead what I'm gonna do is fix up final header at the end of the write by just rewinding the file back to the beginning and then doing an fwrite, and that should work. I think the size is not truncated in that way. And this will write the updated like sizes of bytes and stuff. And so then when the header says that the file is compressed, instead of the reads, we need to decompress the data. So I guess we are gonna add read. How did I call these? Right, vertex compressed. Okay, so we're gonna do read vertex compressed. And then the size and count are the same. Okay, and so then instead of this memcopy, we are gonna do mashup to decode vertex buffer, which, hold on, destination count size, buffer size. Right, we need to pass the actual compressed bytes, the number of them. Because it's used for like bounce checks and whatnot. And then we need to advance the file offset by the compressed number of bytes, not the decompressed number of bytes. So this is straightforward, and then it doesn't compile because what? Because the type is unsigned char. And then the index data is the same. Yeah. The one thing about the index compression is if you want to mix 16 and 32-bit indices, you have to split them up, because when you decompress, you have to decompress either 16 or 32. But we aren't doing, like we are always 32-bit right now, so it kind of doesn't matter for this use case. But yeah, so there's like details that may differ in different engines as they integrate this. But all right, so if the header says that the file was compressed, then we are going to do read vertex compressed, and then we have to pass the compressed vertex bytes, And then the same for index data. Or actually, I'm just gonna okay. Read right without the size off because it's no, yeah, it's fine. And then finally, we can finally run this. I'm getting a little tired, but it's been 3 hours, so that makes sense. I wonder if the streams get easier to do or harder, or like the same if you do them more often. Okay, so I don't know. Let's let's run this and see what happens, I guess. I'm gonna run this from this. Oh, I have an environment variable, right? So right now it's just gonna be uncompressed. And hold on. One more thing before we actually, this did not run the new code. One more thing before we do that is if we are using compression, then it would be nice to print the actual like number of bytes. And then same here. Okay, and then same here. I'm probably gonna remove this ray tracing data thing in the future, but I think for now it's easy enough to try to compress it and see what happens. I've never tried this before. Okay, so if we remove the cache, wait, and right, can you, if you do -f, it returns 1, I guess. Okay. All right. Wait, why? Hold on. I think I broke something. Oh no, I removed the GLTF file. Hold on. It should be in Git. All right, let's do this again. Okay. I don't know if this will work because maybe I typed it something. Right, this is the uncompressed version. So now the question is, if we enable compression, do things break? Because I mistyped something. Wow, I did not mistype anything. Okay, so the code works. Amazing. Okay, that's pretty reasonable. So the I should have like written these down, I guess, but let's just do I should have written down the number, which was basically the Z standard number for just vertex data plus index data, because I didn't. But what I did do is I noted that it was 3x. So, oh my God, calculator. So 26 and 6 plus 4682 is the total. So the standard was around 24.52 compressed megabytes on disk for vertex and index, and mashup is 2328. Okay, so size is a little bit smaller than the standard. And then if you run the standard on the results, it can compress it like more. It's kind of funky in that way. And then let's just profile the data and see if it's like decently fast. I don't know, it should be decently fast. After the compression, the uncompressed meshlet data is kind of more obviously a problem, right? Because before compression, vertex data, I guess even before compression, vertex data was like as large as the meshlet data, but now the vertex data is like smaller on disk. I should note the vertices in this project have been well optimized in prior streams. So, you know, these are like pretty good numbers. And then all of the index data is with level of detail, which amplifies it because there's only one copy of every vertex, but there's multiple copies of indices in certain cases. Okay, and the meshlet data compresses quite well, or the meshlet RT data. The meshlet data should not compress very well. Okay, all right. I'm really glad I don't have to debug this code because I'm tired. Let's profile this. Hopefully it's fast enough ish, and then you know, and then oh, it rebuilt the scene. Why did it do that? Oh, is this it's a different file. Hold on. Oh, this is actually kind of funny because now I have two files, one compressed cache and one uncompressed cache. And so the compressed cache in total, in aggregate, is around 2 times smaller. The data that we did compress in aggregate should be around 3 times smaller. But of course, we didn't compress the meshlet data. And so any data that you don't compress starts getting like larger and larger proportionally. So the aggregate cumulative size reduction is just 2x. We can, out of curiosity, ask, can LZ4 or the standard compress this data further? It would be cleaner to do this experiment without meshlet data in it, but I'm tired. I don't want to do this. So let's just, you know, look at a number. Okay, so LZ4 can still compress it like 30%. Oh, and the decompression of LZ4 is like faster from the compressed data. Anyway, it's at some point a funny, there's a bunch of like interesting nuance around all of this stuff. But yeah, so if you wanted the data to be even smaller, you can post compress with Z standard and you'll get a smaller version of the file substantially. So versus if you just compressed with Z standard, because the standard compressed the whole original file. I mean, I have this here, right? Yeah, so like if you take the uncompressed cache, the standard compresses it to 43 megabytes. If you take the pre-compressed cache, the standard compresses it to 30. So you can, if you wanted to take the hit of the standard decompression, you can compress even further. And then it even works with LZ4. So LZ4 pre-compressed cache is 71 megabytes. LZ4 post-compressed cache is 40 megabytes, and it's also faster to decompress with LZ4. So anyway, all of this is pretty good. So yeah, let's look at the profile. I just need to switch the file name, and then I'll look at the chat and answer questions and stuff. All right. But this was the goal. Let me actually run this again, just in case. Once you work with multi-gigabyte, this is not a multi-gigabyte file, but whenever you work with things that involve the page cache, there's always difficult questions about, oh, is my file still in the page cache or not, right? Okay, so the decoding, the decompression takes time. This is not free. This was 46 milliseconds, I believe, and now it's 76 milliseconds. However, the interesting question is actually not this. The interesting question is if the disk cache is cold, is the loading faster or not? Because of the vector nonsense, there's ways to like hide the cost of all of this decoding stuff in better ways. We aren't overlapping. We are overlapping some costs, but there's. So anyway, you can push this like further. In some sense, Why is there a mem of? All right, this is the uncompressed buffer with meshlet data. Yeah. So the decompression is not free. It's decently cheap. It's as I was saying, it's around LZ4 performance level in aggregate here, I think. So it should be like 4-ish gigabytes a second in aggregate between vertex and index data, I think. Multiple times faster than the standard. But the thing I was saying earlier about the compressed data on disk, right? Let's try to validate this. So again, the theory is this. So we now have two cache files, which is very convenient, accidentally so. One compressed, one uncompressed, and we can load either one. If the page cache is empty, so if the file is not cached in memory, then what we are hoping for is this. Yes, there's a little bit of an extra cost to decompressing the data, like 40 milliseconds or whatever, 30 milliseconds, right? But the hope is that because the SSD is slower, we still save time, because the time to load the data from the SSD is much smaller because the data is much smaller, right? The file is half the size. So the hope is it takes us half the time to load the data from SSD. It takes us a little bit of time to decompress, but also because we use memory mapping, the decompression is overlapped with the actual I/O operations to some degree. And again, there's multiple flags and tricks to speed it up further, which we don't have time for today. And so the hope is overall this is worth it. The only way to check is to drop the caches. So if the audio like pauses again, you know, and takes a little bit of time to resync, it is what it is. Okay, so I've wiped the page cache. Let me look in chat. Z standard doesn't entropy hack, because of that Facebook did Z standard 2, which was eventually released on this strong, where you manually specify transform graph. Are you sure you're getting, so there's a thing that Facebook released which is called some open data standard thing, I forgot, there's some weird name, where there is a transform graph. Are you talking about this, or is this strong something else? I'm not sure what entropy hack is. What about RTX.io? Yeah, so we are not going to do RTX.io. RTX.io is kind of interesting, but it's deflate based, so it doesn't do, from the compression ratio side, it's not as strong as the standard. And then it's NVIDIA specific in some ways. So anyway, I maybe at some point we'll explore this. I don't love, my understanding of the situation around the vendor specific graphics data compression right now is it's like weird. NVIDIA doesn't have hardware for it, nor AMD, as I understand. So it's like a bunch of stuff in the driver, a bunch of code in the driver, and it's different between different vendors. So like, what should I do? Should I compress the scene cache twice for two different vendors with different settings? Come on. Okay, so let's try. So I wiped the cache. In theory, neither of the files should be in the cache, and I should be able to just run the code twice on decompressed data. Let's start with this, and then on compressed data, and then look at the time. Okay. And then the compressed version. And both of these should be called loads because, again, neither file is in cache, but now that I've loaded them, both files should be in cache, so, you know. All right, the moment of truth. That's too fast. Did the page cache thing work? So the good news is the code is faster. And it's both I/O bound. It sort of makes sense that so the compression does speed things up. It speeds things up a little bit insufficiently, you know. the speed up is not that good. It's not 2x, right? Like you would expect close to 2x because of half the data. But I think the issue is, so on these, it's like what I was saying originally earlier, my SSD is like faster than, it still should help even if we could optimally use my SSD, especially if we used multiple cores. But the times I'm getting from my SSD are not just a function of the amount of data that I read it from, because like, you know, times don't line up. Like if the SSD decodes at like 3 gigabytes, if the SSD supports read speeds of like 3, 4, 5 gigabytes a second, but you're reading at 1, there is like complicating factors. And I think complicating factors probably mean that it takes less than half the time, or like more than half the time to read half the data, if that makes sense, right? Like you're having the data, but you're not getting the all of the benefit of having the data. If you're reading from a slower SSD, then, you know, like things would be better. But yeah, okay, so, but anyway, so compressed loads are faster if things are cold. But we are still roughly decoding at around a gigabyte per second from the SSD, because, you know, because there is some software complications in the SSD. And actually we can look at, so we haven't really looked at the mmap from SSD. This is what it looks like, right? So there's some vector nonsense that I already talked about at length, but then we're actually reading the data. We do a mem copy in the uncompressed version, or in the compressed version, we do the decode, the decompression. And then it accesses memory, and at some point that access triggers the actual I/O operations, right? In the when you are just copying, all of your time is just waiting on the I/O. When you are decoding, it's a little bit better, because there's still time waiting for the I/O. So like here we can see that the I/O can't catch up to the decoding process, because it's slower. So that makes sense. But what does happen is that we are getting some amount of sort of free compute, because we are decompressing the data, and in parallel, hopefully, the drive reads some extra I/O, some extra bytes from disk, because it does this predictive load. Like you load 5 bytes, and it will load ahead like 64 kilobytes at a time. Now the problem is, the number is literally 64 kilobytes. Somebody was asking about large pages. Large pages don't really work for I/O in Linux still, and probably will never work, I'm not sure. So like what this means is you load, and I/O, my recollection is that there is, so the page size is 4K, but there's a different concept called the read-ahead buffer in Linux kernel. My recollection is that the read-ahead kernel is like either hard-coded as 64 kilobytes or something like this. And there is a POSIX sequential advice hint that you can give it, in which case it doubles it, so it becomes 128 kilobytes, which is cute. But if you want to read a 100 megabyte file to completion on modern SSDs, 128 kilobytes is too small. And unfortunately, even if you don't use mmap, it's still difficult to get large reads from the SSD controller because of how things are cached. So it's a whole kind of worms. It's actually difficult to read like a large file, you know, from disk at speed. But like the good news is, for example, if we had time for, which we don't, we could, for example, decompress vertex data and index data in parallel now, and it will be half the time, because, you know, we have headroom in the underlying hardware. It's just that there's a bunch of stuff in the software stack that are impeding maximum load performance. But even with decompression from disk, half the time is spent just resizing state vectors. And we could remove this if we directly decompressed into the either Vulkan system memory buffers or ideally Vulkan GPU memory buffers. But we are not going to do this today because I'm tired. All right, cool. I'm gonna commit this code. This worked well. Yeah, don't page fault 50 gigabytes if you can avoid it. Yes, OpenZL. Cool. Yes. Okay, now we are on the same page. Yes. So yeah, so Facebook released a thing called OpenZL, which is it's like a way to compress structured data more effectively than the standard does it. But it's I haven't actually tried it. I tried it a little bit, but I didn't try it sort of extensively enough to comment on it. But it's not as straightforward to integrate at all as the standard is, or LZ4 is, or Meshoptis for that matter, because like it requires data analysis and preparation and building these graphs and serializing them and deserializing them and whatnot. My understanding is it's a good fit for data center use cases where you have a bunch of binary data and like it's structured in weird ways and you can just offline analyze it and then build a recipe for compressing it and then compress and decompress. And all of these things don't require you to write code because they have special modes for how to analyze data without writing C++ code at least. And so it's useful in that sense, but yeah, I wouldn't recommend that for game data. For game data, the standard is good in some cases, LZ4 is good in some cases, Meshopt is good in some cases. Okay, so that's kind of what I have for today. We have done basically all of the geometry stuff that I was planning to do. We now have an optionally compressed cache file. I'll probably enable compression by default. It's like disabled by default right now. You can, maybe the code compiles on Windows, maybe not. And then the thing that's broken is animations. So I'll fix this at some point, maybe off the stream, because at this point, once you've serialized like 5 vectors, serializing vectors 6 and 7 is not that hard. It's just that the animation vectors are like like they're nested. There's like a vector of vectors, and that's a little bit annoying, but it is what it is. Yeah, and then in the normal workflow, or even off disk, which is interesting. So when we started, right, we had 2.6 or 2.7 seconds of geometry loading from cold cache and 2.4 or 2.5 seconds of loading of texture data. Now, even from cold disk, the numbers are more proportional to the sizes of the data. We have 100 megabytes of cache or like 50 megabytes of compressed cache or whatever. They load it like in 100 milliseconds. But then we still have like, oh, this is repeat run. Oh, the images, of course, the textures in the second run are in cache. Yes. Hold on. So in the first run, the textures were also not in cache. So the cold run, shift click. So shift click. Oh, if you hold shift, it writes the number. Very nice. Okay. Yeah. So oh no, but you have to shift click. You can't start pressing shift after you've shift click. Okay. So yeah, so 2.7 seconds of image loading, right? So it used to be that geometry and image loading is the same when cold loading. But now, even when cold loading, the geometry loading is very fast, but the image loading is, of course, slow because it is a gigabyte of data, right, if I recall correctly, loaded from a bunch of different files and uploaded to GPU in small chunks and all of this stuff. So all of this can and will be optimized, but that will not be today because I am done. Okay. Thank you everyone for stopping by. I'm not sure if I have time next weekend. I want to do one more stream on like the IO textures and loading things directly into the Vulkan buffers and all of that stuff. I'm not sure if it's gonna be next week because I need to figure out Christmas schedule and stuff. But you know, socials. However you found out about this stream is gonna be the same way how you'll find out about the next stream. All right, thank you and bye.